In this video, I'm going to start with number 15. A boat with a water speed of 60 feet per second is to be used in a river, which has a current of 20 feet per second going south. Okay? What is the resultant velocity if the boat is headed north? Okay? So boat is heading north at 60 feet per second, but the river is going south, so you do head to tail again at 20 feet per second, and this is feet per second. Your resultant is right here. It's connecting the very first origin to the last arrowhead, and that should be 40 feet per second. That's an easy one, right? Or you can just do 60 minus 20. 60, since north is positive, south is negative, we just do 60 minus 20. Okay. What is the resultant velocity if the boat is headed east? So the boat is going east at 60 feet per second, but the river is going down, or south, I mean, 20 feet per second. So you have to do head to tail, and here is your resultant. And you have to figure out what that angle too is. So to find the resultant, you do Pythagorean theorem, and then you should get an answer of 63.25. And to find this angle, I'll call it theta here, you're going to have to do the inverse tangent of 20 over 60. And you should get an angle of 18 degrees, and it's south of east. You can probably see that in there. All right, for number 16, I'm going to do it two ways. I'm going to do the vector resolution. I'm going to do law of cosines also. All right, so here we go. So for Chris, it falls south of east. So here is Chris. And this angle here is 20 degrees. Okay? Maybe I'll so here's Chris. So I'll make the triangle. So here's the x component for x, and here's the y component for x. So for Chris. And this angle here is 20 degrees, and this is 34 newtons. Okay. And then we have Rob. It's going north of east. So Rob is this way. Yeah. Okay. So here's the x component. Here's the y component. So this is 28 newtons. And this angle here is 55. And that's it. Okay. So now if we look at, I'm going to put C for Chris and R for Rob. R for Rob here, because then this is the resultant. So for Chris, it's going to be positive and negative, because it's right and down. For Rob, they're both going to be positive. Now if you do a little bit of trig here, these are the numbers you're going to get. I'll add into it. So for Chris, it's going to be 34 cosine of 20. You can figure out what that number is. And 34 sine of 20. Okay. And for Rob, it's going to be 28 cosine of 55. Okay, it's this one. This is Rx. And this is R. This is Rob. Rob Y. Okay. And this is going to be 28 sine of 55. Now you put that stuff in your calculator, and you add, you should get 48 here. And 11.31. Yeah. Now, basically, it's positive and positive, which means the x component is this way. So you always start with the x component. It's 48. The y component is 11. Oh, going up. 11.31. Here's your resultant. Okay, so you can do Pythagorean theorem. You can figure that out, and you can get this angle here, theta. So after you finish, you should get 49.31 newtons at 13.26 north of east. I'm going to try to do the same one, but this time using law of cosines. Okay. So we have, okay. So I'm going to go with, I don't know which one I'm going to go with. I'll go with, I start with Chris. So Chris is going south of east. It's 20 degrees. And I'm going to try to do this to scale as much as I can. So this is 34. This angle here is 20. Then I come to the head here, and I do 28 degrees, 28 newtons, but at 55. So it's a sharper angle. So I'm just going to say that's 28 newtons, right? Okay. My resultant is right here. Okay? Law of cosine is quicker, much quicker. But only if I can figure out what this angle is here. Okay? Now, I think we can figure that out. See? This angle here is 20, which means this angle is 20. Okay? They are alternate interior, right? This angle here is 55. So now you get 20 plus that question mark plus 55. That should add up to 180. So that question mark should be it looks like it's 105 degrees. Now here's how the law of cosines works. R squared equals 34 squared plus 28 squared minus 2 times 34 times 28 cosine of the angle facing what you're looking for, 105. And then you can take the square root out, and you can take the radical of all that stuff. So let me try that. 34 squared plus 28 squared minus 2 times 34 times 28 cosine of 25. Take the square root of that, and we get 49.32 newtons. I think earlier I said 49.31, pretty close. Now the next thing we have to do is we have to figure out what this angle is. Okay? Now this is 105 here. Now I'm going to do law of sines. And I'm going to try to find this bigger angle. And once I find that, to find this small angle here, let's just call that theta, I can subtract 20. So I'm going to do law of sines for that. Now this is 49.32 newtons, right? So sine of 105 over 49.32 equals sine of this big angle here, I guess I call it phi, over 28. Now this angle here is 33.25, or it could be the supplement. So you have to be careful. Sometimes it could be the supplement. So 180, the supplementary angles have the same sign. Or it could be 146.75. Okay? Now I think the second one is not an option. Because if I make this 146 and this is 105, I'm already past 180. So that one is out. But sometimes that one works, but this one doesn't. So this is 33.25. You take 20 away, so you're left with 13.25. And I told you earlier the angle was 13.26. And it's north of east. All right, let's look at this tug of war problem. Now, if you have more than two forces, you cannot do law of cosines. Well, you can, but it's just complicated. Okay. So I'm going to write the x and the y, and I'm going to write the components. So this is Jane, this is Joe, and this is Tom, and this is the resultant. Okay. So Jane is going north of east. So Jane is like this. This is the x, this is the y. Okay. Now, it's positive and positive. Joe, north of west. So this is Joe. X and y. Okay, so negative and positive. Tom, it just goes straight south. So this is Tom. So basically, there's nothing in the x component, and it's negative in the y direction. So this is basically just 32, but negative. Okay. Now for Jane, this angle here is 45 degrees, and this is 35. For Joe, this is 30, and this is 45. So if we do the math here, this is going to be 35 cosine of 45. This is going to be 35 sine of 45. This is going to be 30 cosine of 45. See how I did put the plus and minuses first? This one I don't forget. 30 sine of 45. If we add, oh, I got this in the wrong place. This is 0 and negative 30. So if I add, this is what I get. I get 3.54 positive, and I get 13.96 positive. So all I have to do now is just make the triangle. So it's positive 3.54, go down this way, and that's 13.96, and that's positive. What am I doing here? This is 13.96. Okay, and we have to figure out what this R is. So if we do Pythagorean theorem, we can also figure out what that angle is. So if you do Pythagorean theorem and you do the inverse tangent of 1396 over 3.54, you get an angle of 75.77, about 76 degrees, and R is 14.40 newtons. Okay. All right. The next question says, what force should Lindsay exert so there is no winner, right? Now, the winner here is basically going to be the one that's going to be closest to the resultant. So you just go back and figure out which one is closest to the resultant. Now, Lindsay has to actually apply a force equal to the resultant. So this is Lindsay, right? Okay, and at that angle. So she should apply 1440 newtons at 76 south of west. Okay, so in order to have a tie. There's a plane going west, but because of wind, it ends up going northwest. Okay, so there is a 25-degree north of west. That's the direction that the plane is going. And for this problem here, we're trying to find the speed of the wind and the direction of the wind. All right, so we're going to try to do this two ways. We're going to do it with the law of cosines, which I think is quick. So to do law of cosines, we're going to do 285 squared, W squared, equals 285 squared plus 400 squared minus 2 times 285 times 400 cosine between the 285 and 400. And then after you're all done, you should get a W equals to about 186, 185, 198 to be exact, miles per hour. Now, to find the angle, I'm going to try to go after this angle. And once I'm done, I'll figure out this angle here with respect to the west. So to find out what this angle here, let's call it theta here, so it's sine theta over 400 equals sine of 25 over the 185, 198. And if we do the math, we get theta equals 65 degrees, about 65 degrees. Okay? Now, it could be 65, or it could be the supplement of 65, which is 115. That's when you have to go back to the triangle and see which one of those two makes sense. Yeah, I don't think the 65 makes sense because, let me just record this. This is 185, 198. Okay? So if I put a 65 here, okay? And this angle here would be, what is that? 90. Okay? Now it looks like I have 400 across from 65 and 285 across from 90. That doesn't make sense. Because across from the 90, I should have a bigger angle, a bigger number than 400. So this has to be 115. Okay? Which leaves us with 65 here. Okay? Because that's 180. So the answer should be 185.98 at 65 degrees north of west. Okay, so that's one way of doing it. Now let's look at the other way, which is basically making a chart. So in this case here, this is a little different than before. In this case, we do have the resultant, right? And we have to find components for the wind. And we have, this is 285, and we have information about the 400. So the plane is going to the left, so this is a negative. This is 0, there's no y component. We have to find, I guess I call this Wx and Wy. And for the 400, it's negative and positive. So negative here and positive here. Right? Now you can take this 400, right, and make it a triangle and figure out the components here. So this is going to be 400 cosine of 25. And, oh, not there. 400 cosine of 25 here, and 400 sine 25 here, and this is just going to be negative 285. Okay? Now basically, negative 285 plus Wx should be equal to negative 400 cosine of 25. And the other equation should be these two added together, 0 plus Wy equals 400 sine of 25. And I think once you find the components, you get Wx is equal to negative 7752 miles per hour, and the Wy equals 169.05. Okay? And you make a triangle. So this looks like it's left. We start with the x components first, and you do head to tail. So you go left, and you go down. No, you go up. Left and up. Okay, so this is 7752, and this is 169.05. And you just have to find out what this W is. So you can do Pythagorean theorem, you can figure that out, and you have to find this angle by maybe doing the inverse tangent of 169.05 divided by 7752. And you should end up with the same answer. Okay? So, and you only do this law of cosines if you have, if you're only dealing with triangle. Okay? And you have to pay attention, be careful with this. When you find the angle, you have to go back to the triangle and make sure that it does make some sense. All right, let's see which one of these people is right. We'd have to know the direction of the vectors to know how big the resultant is going to be. Okay? Where it says, since we are only asked about the magnitude, we don't have to worry about the direction. Well, in vectors, direction is extremely important, so that's wrong. Okay? This person is wrong. We have to know the direction of the vectors to know how big the resultant is going to be. Alexis is correct. Direction, you have to know the direction and the magnitude. And you already have the magnitude of both. Okay? And Kara says that you can just use the Pythagorean theorem. Well, we don't know if they form a 90-degree angle, so we can't go by that. Okay, the resultant is the vector that you have to add to the first vector to get the second vector. That's not true. Okay, this is not one-dimensional. It could be in any direction. So the bottom line is that the answer for this problem here, I'm just going to sidetrack here, is anywhere. The magnitude is anywhere between 2 and 8. Somewhere between the difference of this 5 and 3 and the sum of 5 and 3. All right, let's look at this last one here. So the magnitude is less in case A. And here's the reason. The x component in both cases is going to be 0. The x component of the resultant. Because if you take this and you project it here, and you take this and you project it here, they're going to be equal and opposite. And you're going to end up with the same thing on the other side. Now, if you take this 3 and this 3 have the same angle as the 6 and the 6. Okay? But this 3 and this 3, even though their x components cancel, but they're going to have a bigger y component than if you place them here. Just think about like taking this 6 and breaking it into 2 pieces, a 3 here and a 3 here. And do the same thing here, a 3 here and a 3 here. Okay? So this 3 and this 3 are kind of like here. So this will give you the same y component of the resultant. But these 2 here will give you something more vertical because they are closer to the vertical than these 2. These 2 are not vertical, or are not as vertical as these 2 here. Okay, so that's if you want to do it with conceptually. Now let's see how we can do this with the math. Now for this guy here, the y component would be 6 sine 45. Okay, you're looking for this. We already said that the x components cancel out. But you have this twice, so 2 times that. Okay? Now let's look at it here. You have 3 sine of 45, and you have that twice, plus, that's from these 3's here, and you have to do the y component for these 3's, right? Basically doing this component here. That's the y. And that's 3 sine of 75 times 2. Okay? And if you do the math here, I think we don't have to compare the 2's here. If you do the math, you're going to find that this number here is less than the number. Okay, so you can do it either way. All right? Thank you. Hello. So for this video here, we're going to start on page 2. So I'm going to show you how to solve the problems. One thing I want you to be aware of is that if you want to find the average speed, and you're given different speeds for a trip, so in other words, if you're going for 1 hour at 58 meters per second, and for the next 2 hours, you're going at 30 meters per second, and for the next hour and a half, you're going at, 20 meters per second. To find the average speed, you cannot just take these speeds and divide by 3, because these rates are happening for different times. Okay, so just make sure you're aware of that. If they were happening for the same amount of time, then yeah, you could do that. All right. Suppose an ostrich runs 1.5 kilometers at a speed of 58 kilometers per hour, and then runs another 1.5 kilometers at a speed of 29 kilometers per hour. What is the speed? The ostrich's average speed. Okay. So average speed is total distance over time. Well, the total distance here is 3 kilometers. Now, how long did it take to do this 3 kilometers? I think we can use the V equals D over T for each part of the problem. So in this case here, the T will be D over V. So it's going to be 1.5 divided by 58. So I should do 1.5 over 58 here. I get a number. Okay? I'm sorry. And add time for the other part of the and add the time for the other part, so that's going to be 1.5 divided by 29. Okay, so I'm going to try that on my calculator. So 1.5 divided by 58 plus 1.5 divided by 29. And I'm going to do 3 divided by that number. My answer is 38.67. And that's in kilometers per hour. So I'm going to leave it in kilometers per hour. All right, let's look at number 2. Sally travels by car from one city to another. She drives 30 minutes at 80 kilometers per hour. So just be careful with the mixed units here. We're talking about hours and we're talking about minutes. 12 minutes at 105 kilometers per hour and 45 and blah, blah. And she spends 15 minutes eating. So even if you're resting, you have to include that in your speed. Okay, so you have to include that in your time, basically. Determine the total distance traveled. So what you have to do is that you have to take each part of the trip and do V equals D over T for each part, okay? And find the distance. So basically this means that D is V over T. And you do this multiple times. So the V here is 80, but the time is half. So that's 40 kilometers. That's half an hour. The V here is 105. The time is 12 over 60, so that's 1/5 of an hour. And that should be 21 kilometers. And for the last part, you're going to do, what is it? You do 40, yeah, 40 times 45 minutes is 3/4 of an hour, so that's going to be 30 kilometers. And you just add this, and you should get 91 kilometers. Okay, so for this part here, it's 91 kilometers. Now to find the average speed, you take the average, the total distance over the total time. Well, this is 91 over the time here is 30 and 20 and 45 and 15. So how much time is that? That's 60 and that's another 50. So that's 110. It looks like that's what it is. Yeah, 110 minutes. So I'm going to do 110 minutes divided by 60 to get time in hours. So it's 91. Okay. I think I missed something. Okay, 30 minutes. Oh, not 20, 12. That's what I missed up. So that should be, I think should be 102. Okay, so let me try it again. 91 times 60 divided by okay. Let me just add this again. This is 42 and 60. Yeah, 42 minutes. 45, so that's 60, 72, 102. 102 divided by 60, that's my time. That times 91. So I get 53.53 kilometers per hour. Okay. I talked about the velocity in the first video of this speed and velocity video, part 1. So we're going to try to do number 3. Ellen walks 3 miles east. So she goes this way, 3 miles. She makes a 40-degree left turn. That's from her perspective. So she kind of like turns this way. This angle here is 40. Okay? And she goes for another 2 miles. Okay? And she does this in 52 minutes. And she does this part here for 30 minutes. Okay? What distance did Ellen travel? So with distance, it's pretty straightforward. It's 3 plus 2, which is 5. What's her speed? Well, you're just going to have to do, in miles per hour, you're going to do total distance, which is 5 over total time, which is 82 minutes. But to change it to hours, you divide it by 60. So it's going to be it's going to be 3.66 according to what I have here. 3.65. So 3.66 miles per hour. That's her speed. Now, her displacement is a different story. So to find the displacement, I'm going to get rid of that. So if this angle here is 40, This angle here is 140. Now her displacement is this line that I'm going to draw in red. So that's her displacement vector, right? So to figure that out, I can do law of cosines or I can do the chart, and I'll show you both ways. So to do the law of cosines, which I think is easier in this case, it's going to be 2 squared plus 3 squared minus 2 times 3 times 2 cosine of 140. And you would take the radical of that and get rid of this squared. So if you do it that way, you should get, what is that, 9 plus, that's 13. 13 minus 4 times 3, that's 12 cosine of 140. And I'm going to take the square root of that. So I get 4.71. 4.71 miles. Okay? Now, I need to figure out this angle here, so I'll call it theta. Okay? So I'm going to do law of sines. Sine of theta over 2 equals sine of 140 over this distance here, which is 4.71. So with the math here, we should get 2 sine of 140 divided by 4.71, and we take the inverse sine of that, and the angle is 15.83 degrees. Okay? Now let's see if that makes sense. Well, if this is 4.71, this is 15.83, so what's left here? So what is that? 155.83 minus 180. So this other angle is 24.71. So I think the triangle makes sense. Okay? You have 140 and you have the longest leg across from it, etc. Right? Okay. And we have to say at 15.83 north of east. Okay? I said 15.90, but that's close. Okay, now let's look at it the other way. The other way you would have to take your 2 displacement and break them down. Here's the 3 miles, and here's the 2 miles. And this is the resultant that I will call D. This is the X component, this is the Y component. For the 3, it's positive, and it's 0 here, because it's just going to the right. For the 2, it's positive and positive. Okay. So for the 3, it's basically just positive 3 here and 0 in the Y. For the 2, it's 2 here. This is the X component, this is the Y component, this is 40 degrees. So this is basically going to be 2 cosine of 40. And this is going to be 2 sine of 40. So let me see what that is. Okay, 3 plus 2 cosine of 40. So this is 4.53. Okay? And 2 sine of 40 is 1.29-ish. Okay. So and they're both positive, which means I'm going to be going in the northeast direction. So I make that triangle, just like we did in vectors. In the vector series. 4.53 here, 129 here. Find out what this D is here and find out what that angle is. So you can do Pythagorean theorem, okay? And you can do the basic trick to find the angle. So I got 4.71. I think that's what we found earlier. And for the angle, I do second tangent. In other words, the inverse tangent 1.29 divided by 4.53, and I get about 15.90 degrees, which is close to the answer we got earlier. Okay, so it's about the same thing. Now to find the velocity, okay, the velocity is displacement over time. So if I take the vector displacement and I divide it by time, which is positive, the direction of the vector does not change. Okay, so basically V and D have the same direction. So I don't have to worry about the angle. If I want to find the V, all I have to do is take my displacement, which I think was 4.71, and divide it by the time after they change it to hours. Okay? So the 52 minutes added to 30 minutes, that's 82 minutes. You divide it by 60 to get that in hours. Okay. All right, let's look at number 4. A plane is flying due south at 500 miles per hour for 2 hours. The pilot, okay, so it's going in this direction for 2 hours, makes a 60-degree right turn from his perspective. Okay, he turns right. Okay, he travels for 550 miles per hour. I mean, at 550 miles per hour for 90 minutes. Okay, so I think we have to figure out what this distance is here. So if we do vehicles d over t, this is going to be 1,000 miles. The other one is going to be 550 times 90 minutes, which is an hour and a half, times 1.5. This is 825 miles. Okay. Find the plane's speed and velocity. Speed is easy. Speed is distance over time, total distance. So it's 100 plus 825, so that's 1825. Now, how long did it take to do that? 2 hours and an hour and a half, 3.5 hours. Okay? In the question, I think it should have said, find the plane's average speed. Yeah. And I'm going to divide that by 3.5 hours. And I got 521.43, close to what I have. 521.43 miles per hour. Okay. Now I'm going to try to find the velocity. Now the velocity is displacement over time. So now the displacement is basically the direct line that connects the very first starting point to the very last destination. So this is the displacement vector. So how do I figure that out? Not a big deal. So this angle here is 60, which makes this angle here 120. So now we're going to do the law of cosines. So I'm going to do d squared equals 825 squared plus 1,000 squared minus 2 times 825 times 1,000 cosine 120. And I can just take the square root of that, basically. Okay? So that's going to be, all right, 825 squared plus 1,000 squared minus 2 times 1,000 times 825 cosine 120, and I take the square root of that, and I get 1582.92 miles. Now to find the velocity, I just take that number, okay, and divide it by 3.5 hours. So if I divide that by 3.5, I should get 452.26 miles per hour. Let's hope that it's right. Yep, it is. Now we have to find the angle. And I need to find the angle always with respect to east or west. So I have to find this angle here. But before I do that, I can find what this angle is. Okay? So I'm going to do law of sines for that. So sine of this angle is question mark over 825 is sine of 120 over this the d here, which I found earlier to be 1582.92. So this question mark angle is, so I'm going to do 825 sine of 120 divided by 1582.92. Take the inverse sine of that. So it's 26.83. Now, this theta and this question mark are complementary angles. So I'm just going to subtract that from 90. And this angle here is 63.17 degrees. Look at my answer key. That's what it is. Now here I have to add. See, a velocity with that direction is incomplete. at, what did I say? I say 63.17 degrees, and you come back here and look at it. It's towards the south direction from the west. So south of west. Now we're on page 5. Okay. Now to do these problems here, what you need to do, you have to take each phase of the trip, and I'm going to cheat a little bit here. I'm just going to see how I broke this down. So I broke it down by 2. Each box is 1, basically. 6, 8, 10. Now to figure out how you break it, and that's basically, I'm looking at the total, the whole time that I traveled. So I did 4 seconds and 3 seconds, that's 7, and 2 seconds, that's 9. So I need at least 9 seconds. How much distance do I need? Or how much distance did I cover? I covered 100 here. Okay, starts for 3 seconds, so nothing is happening, and then you cover another 80. So I cover 180. So I cover 180. So I have to make sure that I can fit at least 180 in there. So I broke this down by 40, 80, 120, 160, and 200. Now, how do we graph this information? Okay. So in the first 4 seconds, after 4 seconds, I should be at the 100-meter mark. So 4 seconds, 100. Just do this. The ruler, of course. Okay. Okay, that's what it should look like for that part. Okay. Now, for the no, I did it in the wrong place. It should be here. Okay. For the next 3 seconds, nothing is happening. So between 4 and 7 seconds, nothing is happening. So you're not moving. And then, after another 2 seconds, I travel 80 meters from the 100. So I should be at the 180 at 9 seconds. So here's 180. That's what I should be. Okay? And all the other ones are kind of like that. So you just have to go to the answer key and see how it's how they are done. Okay? So I think we can try another one. So let's try maybe number 3, I guess. Yeah, let's try number 3. Okay. Let's see how much time I need. I need 2 and 3. That's 5 and 3. I need 8. So I'm going to 2, 4, 6, 8, 10. So I need to get up to 8. Now, how much distance do I need? I need 60. I stop for 3 seconds, and then I go for another 150. So I need 210. Okay. Now, the way I broke this is that I broke it every 2 boxes is a 60. Yeah. I think that's what I did. Yep. Okay. This is a position time graph. Okay. Now, for the first, after 2 seconds, I should be at the 60-meter mark because I travel 30 meters every second. So after 2 seconds, I should be at the 60. So I should be here. Then I stop or the car stops for 3 seconds. So between 2 and 5, there's nothing happening. Okay? And then from 5 seconds to 8 seconds, I go 150 meters. So it's 150 from the 60. So I should be at the 210. So 210 is pretty much right there. Yeah. Should look like that. So these are considered extremely, extremely easy. Okay? So I think I got that right. Number 5. You are driving home from school steadily at 65 miles per hour for 130 miles. So that should take you 2 hours to complete that trip, that part of the trip. It then begins to rain and you slow down to 55 miles per hour. You arrive home after 3 hours and 20 minutes. How far is your hometown from school? So I think what we should do for this is figure out how long you've been driving for at 55 miles per hour. So 3 hours and 20 minutes is 3.33 hours, repeating. Okay, you subtract the 2 hours that you would drive in at 65. That should give you 1 1/3 of an hour. Okay, and you can figure out the distance by you drove at 55 miles per hour by doing V is d over t. So 55 is d over 1.33 repeating, and that should give you a distance equal to. Okay, I didn't do that, so I'm going to try. So 55 times 1.333333 repeated. So this is about 73.33 miles. Okay, and then you would just take that and add it to the 130, and you should end up with 203.33 miles. That's how long you've been. That's how much distance is your home from school. So you add 130 here, so 203.33. What is your average speed? Average speed is distance over time. Okay, so the average speed is going to be total distance, which is 203.33, divided by total time. It took 3 hours and a third of an hour. So if we take 203.3333, okay, and divide that by 3.33333, we should get about 61 miles per hour. So that's your average speed. All right. Number 6, an airplane travels 2,100 kilometers at a speed of 800 kilometers per hour. The day it encounters a tailwind that boosts its speed to 1,000 kilometers per hour for the next 1,800 kilometers. What was the total time for the trip? Okay, so I think we can do V equals d over t here. So the time for the first part is just going to be 2,100 divided by this marker divided by 800, and that should give us. Yeah, I didn't do that part. Okay, so 2,100 divided by 800. So that should be 2.625. Then you do it for the other part, which is 1,800 divided by 1,000, and that should give us 1.8 hours. So if we add up these two together, plus 1.8, should get 4.425 hours. And you have to show the work, of course. You have to write your formulas and stuff like that. What was the average speed? Well, the average speed is distance over time, total distance. So we did 2,100 and 1,000. I'm sorry, and 1,800. So that's 3,900 divided by that 4.425. And the answer should be 881.36. And that's in kilometers per hour. Number 7. For number 7, it took, you hear the sound hitting the pins 2.5 seconds after you release it. But it took less than 2.5 seconds for the ball to hit the pins, because it takes sound some time to come back from hitting the pins to your ears. Okay? So you have to subtract that small amount of time. So the V of the ball is distance that the ball travels over the time. Or I can do delta x here. Equals, now, it travels 16.5 meters, but it definitely did not take 2.50 seconds. It took 2.50 seconds minus the time it took for the sound to travel 16.5 meters to reach your ears. Just try to imagine that. Now, the time it took for the sound to travel from hitting the pins to your ear, okay, so you do the V for the sound is distance over time. So the time distance, which is 16 and a half, over the speed of sound, which I think they've given us as 340. Okay? So we have to subtract this little bit of time here over 340. And you would put that in your calculator, and you would get, I didn't do it, so it's 2.5 minus 16.5 divided by 340. Okay, and we're gonna do 16.5 divided by that. So speed is 6.73 meters per second. If we did it just with the 2.5, it would be different. It would be 6.6. Okay. All right, let's look at this. These problems are a little tricky, so let's look at number 8. One night at the horse race at the Midlands racetrack, the horse Anti-Science was coming into the final stretch. Was in the lead by 24 feet, racing along at 12 feet per second. When my physicist released that extra burst of, so Anti-Science is here, my physicist is here, okay, and this is the finish line. Okay. How long does it take until the horses are neck and neck? So basically, their position is the same. So I have to follow exactly what I did here. So in here, I thought of this as a number line. So I picked this as 0. This guy is at the positive 24 meter mark, or 24 feet mark. Okay. Now their positions have to be equal at the end. Okay, almost. Okay. So for my physicist, he was going at 16 feet per second for a certain amount of time t, which is the same as the time for Anti-Science. And this one is starting from 0, so plus 0 equals Anti-Science is 12, the same amount of time, okay, plus 24, because it starts at the positive 24 position. So if we do the math here, we get t equals 6 seconds. Okay. How far from the finish line did my physicist, this guy, put up the final effort? So you just have to take this 6 seconds and give it to my physicist. So you do 6 times 16. And I also tried it by setting this position here. So this is going to be 96 meters, it looks like, right? Okay. Setting this as 0, this is going to be negative 24. Okay, so now the x, my physicist, equals to the x for Anti-Science. So for my physicist, it's going to be 16t minus 24 equals 12t. So you can see that the 24 just changed places. So this is going to be 6 seconds. So if you want to find the position of my physicist, that's the position with respect to 0. How far away from the 0 he is. So you're going to do 16 times 6 minus 24. But if you want to find how far he's from the finish line, he's now 24 behind. So you have to add 24. So it ends up being the same thing, no matter what you do. In a bike race, Skylar, the biker, is in first place. Okay. So it looks like this. Skylar is here. Basil is behind her. And she has a lead L on him. Now, he's 200 meters from the finish line. Okay. She's going at 15 meters per second. He's going at 15.62. Okay. What is the smallest lead? Basically, we're trying to find this L, so that Skylar wins. So we're going to make them that they're going to come to a tie, And we just have to say, well, the lead should be just a little bit more than what we find. So maybe I can set this position as 0, basically, right? So I'm going to say x of basal is equal to x of scalar. Now, when basal is at the finish line, his position is 200. Okay. Now, for her, it's going to be 15t, right, plus this L here. Okay, because she starts from a position L, basically, right? I think that's how we did it. Yeah. Okay. And then we say t. Actually, we can figure out what the t is, right? Because we know that he's traveling at this speed and he covers that distance. So I think his time, or the time for both, is the same thing. It's going to be 200 equals 15. The time is the distance over the speed plus L. And you should get an L equals to about 7.92 meters. Okay? You could have made this an inequality, right? You could have said, well, 200 is less. So in other words, her position is going to be a little bit higher. We could have done the inequality and we get L is less than 7.92. Okay. All right. So number 10. Two locomotives 1,500 meters apart approach each other on parallel tracks. All right, so I'm going to draw it here. So one is going at 50 kilometers per hour, and the other one is going in the opposite direction at 58 kilometers per hour. So we have to look at that as a negative. How long will it take them to reach each other in seconds? So I'm going to try this approach here. So I'm going to say, you know what, this is 0. So which means that this one starts from the positive 1,500 meter mark. And they're going to meet here somewhere, right? Yeah. Okay. So when they meet, they will have traveled the same amount of time. Okay. And they will be at the same position also, right? So we can try it this way. So it's 50 t. Okay. So 50t will put this guy here equals negative 58t plus the 1,500. And the reason we put the 1,500 because this guy started at the 1,500. So t equals, now when you find the t here, you're going to find it in hours, right? So it's going to be 1.5 divided by 108. Okay, so to change it to seconds, we just have to multiply by 60 basically, right? So if I do that, so 1.5 divided by 108 times 60, I should get, oh, that's in minutes, so times another 60. So I have to multiply by 3,600, not 60. So this should give us 50 seconds, okay? Another way we could have done this, we can say, well, you know what, the distance traveled by this one plus the distance traveled by this one should add up to 1,500. The distance traveled by this one is 50t, okay, plus the distance traveled by the other one. See, I'm talking distance here, so the direction doesn't matter. That should be 1,500. And you will solve it like this. Okay? All right, let's look at number 11. A tourist being chased by an angry bear is running in a straight line towards his car. So the tourist is here, the bear is here. Okay? Distance d away, so the car is here. So this distance here is d. The bear is 26 meters behind. So I'm going to choose this as 0, which means the bear is at the position negative 26. Okay, so the bear is going at 6 meters per second, and the tourist is going at 4 meters per second. What is the maximum possible distance, the value for d? So I'm going to say, you know what, let's just say that they're going to get there at the same time. Then I will just, whatever value I find for d, I just have to go shorter, because longer means that he's going to catch him. So I just can't, common sense. So I'm going to say x for bear is equals the x for the tourist. Okay. Now for the bear, it's going to be 6t for time minus 26. He starts 26 behind the origin. I chose this as the origin. Equals just 4t. And I think we can solve for t. And t will be 13 seconds. Okay? And then I just take that 13 seconds and plug it in for the position of the tourist, basically, where they're going to be after 13 seconds. So the d should be 52 meters. So technically, it should be less than 52 meters. Okay? Another way we could do it, I can change the origin too. I can make the origin here and make this at positive 26. You can do whatever you want to do. We can say that the time for the tourist has to be less than the time for the bear. Now, the time for the tourist is the distance that he travels divided by his speed. That should be less than the distance traveled by the bear is d plus 26 over his speed. And you can solve that inequality. Or you can make an equation and find d and say, well, it has to be less. Okay. An 18-year-old runner can complete 10 kilometers with an average speed of 4.39 meters per second. So pay attention to the mixed units, right? This one is pretty straightforward. So I think what we have to do is just find the 2 times and subtract. So the t for the younger runner is going to be distance over the velocity of the younger runner, right? So this is going to be average velocity. So it's 10,000 divided by 4.39. T for the old person is going to be the distance divided by the velocity for the old person. So it's going to be 10,000 divided by 4.27. And find out what those numbers are, and you just subtract 10,000 divided by 4.39. So here I got 2277.90 seconds, because it's in meters per second. The other one, I get 4.27, I get 2341.92. So if I subtract, okay, so I get about 64 seconds. Okay, so he has to start 64 seconds later in order to be a time. Okay. 13. Mike leaves his house to school at the same time as his younger sister. He's walking at 2.5 meters per second, and she's walking at 1.7 meters per second. He arrives to school 72 seconds ahead of her. How far is school from home? So I think to do this, we have to realize that the positions are going to be the same at the end. So they both started from home, which I think I can look at that as 0, and they both are going to get to the same position, which is the school. So I think we're going to say, well, x of Mike is equal to x of the sister. Okay. Now, the position for Mike is going to be 2.05 t, but it takes him 72 seconds less time. Okay, so even though it says later or ahead, it means that it took him less time. Equals 2.05 times t, and you would solve this for t, which I didn't. Yeah, I did. 492 seconds. Okay. Now, how far is school from home? You can just take 492 and plug it into either one of these equations, and you should get 861 meters. Okay, that's how you pretty much do this stuff. Now, if you don't want to do it this way, you can try, say, well, his time is t, it's going to take her 72 seconds longer. Okay? So if we solve that equation, we should get, did I mix this up? Okay, this is not supposed to be 2.05. This is supposed to be earth speed 1.75. So you can make that correction. So, so this is going to be 0.3 c equals, what's 1.75 times 72 equals 126. Okay, so t is equal to 420 seconds. Now, if we do it this way, that's the that's the time it took Mike, 420. Okay, so if we take 420 multiply by 2.05, we get out 861. Or you can take 420 and plug it in here. So that's up to you how you do it. Okay, skip. This one here, I think we're just going to do it in class. All right. For number 1 on page 11, you're given a couple statements, and we have to figure out which one of these people are correct. Okay, so this person is traveling for 10 minutes at a certain speed, for 20 minutes at a different speed, and for 15 minutes at a different speed. So Aaron says, I think the average speed of the entire period is 18 meters per second, because to find an average, sum the 3 and divide by 2. First of all, there's something very wrong about that. Like, he's wrong 2 ways. You can't just take them and divide. And even if you divide, you have to divide by 3. But that is still wrong, because to find the average speed, you have to do the overall distance, total distance divided by the total time. You do not just take the single speeds or the individual speeds and add them and divide by 3 or 4. That depends on how many there are. Okay. Bessie says, I disagree. The average speed is 12 because you add 3 velocities, but you then just have to divide by 3. That's wrong. You can't do that, because you have these rates at different times, so it just doesn't work that way. Because the definition of average speed is total distance divided by total time. So Caesar is the one that's correct. All right, let's look at number 2. Now for number 2, I want you to pay attention to what kind of graph we're dealing with, and that's going to be extremely important in this unit. This is a velocity time graph. So in other words, if you want to read the velocities in time, you just go across to the y-axis and read those numbers, and that's your velocity. Okay? You don't do the slope here. If this were a position time graph, then we do the slope to figure out the velocity. This is not the case. This is just read. So if I want to find the velocity for B at this moment, just go up, come across, and find the velocity. Velocity of A at that moment, just go up, come across, and find the velocity for A. All right? So here it says B is faster. That's a wrong statement, because A is always faster, because the graph or the line for A is always above the line for B. Okay. This one is number 3 is a ball thrown up in the air and falls back. Okay, so they're giving us a velocity time graph. Now, if you think about this, basically what this means, it just means that the object, okay, starts with a speed. So when you throw it up, okay, right, and slows down to 0. But when it gets to 0, what it actually does is just continues in that same direction, but faster. Okay, so when it gets to the top, it just continues going up, but faster, which doesn't make sense, because this velocity is always positive. This does not show any change in direction. So the correct way of doing this for this problem here, you have to show a graph, a velocity time graph, that's changing direction. So in other words, you have to have some positive velocities, some negative velocities, and a 0 in between. So this point here is the highest point. So if you think about this, when you throw it up in the air, we're thinking of up as being positive here, okay? Because you start with a positive velocity, and as you're going up, as you're traveling in time, your velocity decreases, okay? It reaches 0 at the top, and it changes direction, and this indicates the change in direction. If we choose down as positive, okay, the graph will look something like that, okay? Because you start going up, and we choose up as negative, okay? So as you go up, your velocity is negative to start with. You get up to the top, it's 0, and you start to come back on the way down, which you consider positive, okay? So that's the reason that one is wrong. Number 4, again, it's a velocity time graph. It's not a position. So if you want to find the velocity of the boats, you just read the values. So I do have values here. I don't feel like doing them again. Okay. So this is a 0. I'm just going to read the value here. This is, I think I said -1, and I guess third or fourth. Okay. This one is about 1.5 positive. Okay. This is about -1/4. This is 0, and this is about positive 1 3/4. I think that's what I have here. Yep. Okay, so the ranking would be FB from greatest, and it looks like A and C are tied for 3rd and 4th place, and then comes which one is bigger? So then comes E, and then comes D. Now here, if they tell us, just to a sidetrack, if they tell us that we're looking to rank the magnitude of velocity, it just means you drop the negatives. So if it says the magnitude, you drop this, you make that a positive, you make that a positive, right? And then you rank them based on that. Okay, but it's not asking you for that. Okay, for number 5, now this is a position time graph. Okay, so here we're looking for speed, not velocity. So which means we're going to find the slope of these curves here, of these lines, and ignore the negative. If it had said velocity, we'll keep the negatives. So you just got to be careful with that. All right. So the slope of this here is, you can do a rise over run, so it looks like it's 1/2 positive. Okay. So in terms of speed, I think I said that this was, what did I say? Drop of 2, so it's 2 over, I guess, 1.5, okay? So which is basically 4 over 3. I think that's what I said. Yeah. Okay. And I ignored the fact that it's a negative slope. This is the slope here is 1 over 6, positive 1 over 6. The slope here is 1, 2, 1, 2, 3, 4. So it's 2 over 4, which is basically half. And when you're doing the slope, always pick the points that are furthest apart. This way, if there is an error, it's minimal. The slope here is drop 1 and run 6. Okay, so I'm going to do 1 over 6. Even I'm going to make that positive because I'm looking for speeds. And here I go 1, 2, 3, 4 over 3. So it's -4 over 3, but since its speed is positive 4 over 3. So the ranking would be C and D. For first place, okay, C and D. Yeah, they both 4 there, so I'm done with this. Then comes A and B. Then comes whatever is left. What is it? E and F. And they are equal. Okay, so you just have to be careful when you're dealing with these problems. You just have to be careful if it's a position time. If it's a velocity time. If it's a velocity time, you just read from the graph to find the velocity. If it's a position time, the slope will give you the velocity. If it's a speed, you drop the negatives. Okay? All right, I'm done here. All right, we're going to start on page 15, number 6. It's giving you an acceleration time graph, and it's giving you a velocity time graph, and it's asking if there is anything wrong with this, and if there is, let's just identify it, right? Well, if you look at, I'm going to break this down into sections. So I'm going to break this into A, B, C, D, So now for part B and D and H, I guess, there is no acceleration. For part A, the slope of this segment here should give us the acceleration. So the acceleration here is positive. The acceleration here is 0. This acceleration should be negative. For D it should be 0. E it should be negative, 0, positive. It's just the slope basically, right? So what's wrong with this picture here is for E, yeah, this part here is good. That's a positive slope. This part here is good. That's a negative slope. This part here is no good. This should be a negative slope. Okay? And for the last part, it should be a positive slope. That's what's wrong with it. Okay. Now, this is a velocity time graph for number 7. It's talking about velocity time graph and acceleration time graph. Okay, so we're going to try to sketch the acceleration time graph. So for the first time interval here, so we have a positive acceleration. So I'm just going to mark it here. Okay, and then it's going at a constant velocity for the next time interval. So drop here, go across the x-axis or the time axis, right? And for the next two intervals, you have a negative slope, but it's not as steep as in the very first part. So it should drop, but it's not going to be as high as for the first part. So it should be something like this. Right? Hello again. Okay, today we're going to talk about interpretation of graphs, motion graphs. In other words, position time, velocity time, and acceleration time. And we're going to see how we can go from one to the other, right? Now, before we start this, I want to talk a little bit again about this PVA that I talked about in the past. So P stands for position, V stands for velocity, and A stands for acceleration. And then let me just write it out down first, and then I'll talk a little bit about it. So what does this mean? This is just a quick shortcut for you guys to know how to analyze these graphs and how to get information out of the graphs. If you have a position time graph, and if you take the slope in that position time graph, that will tell you some information about your velocity. If you have a velocity time graph, if you take the slope, you get the acceleration. Going the other way is a little tricky, because when you do an acceleration time graph, you don't actually get the velocity, but you get the change. So I'm going to put a delta here. So when you do acceleration time graph again, you get a change in velocity. And when you do a velocity time graph, you do a change in position. And a change in position is just displacement. And we talked about all this in the past. So I'm going to be relying on this a lot to analyze some of these graphs. Not here, but later. So here it tells you to replace d with x. In other words, this is not distance, it's position. But in this case, we can say that the distance and the position are the same thing because we're just traveling in the positive direction. So in this here, it says the first line has to describe velocity, second line has to describe acceleration, and the third line has to say what kind of motion. Is it uniform? Motion meaning if you're going at a constant velocity, that's uniform motion. If your velocity is changing, we call that variable motion. And if there is no motion, then there is no motion. All right, so let's look at the first line. I'm going to go back to this. Actually, I can probably use this. If you have a position time graph, the slope gives you the velocity. Well, you look at the slope here, it's a constant slope. In other words, it's not a change in slope. So I can say that the velocity is constant. And if the velocity is constant, there is no acceleration. And the motion will be uniform. I'm just going to abbreviate. If I'm looking down here, it looks like as the time passes, this curve is getting steeper and steeper in time, which means my velocity is increasing. And if the velocity is increasing, I'm accelerating. And if I'm accelerating, I'm dealing with a variable motion. So I want you to pause the video for about 2 minutes. Try this problems here, but I'm going to keep going. So pause the video for 2 minutes and try this. It shouldn't take you 2 minutes, but if you need 2 minutes, it takes you 2 minutes. Here, there is no motion here. In other words, you're stuck in this position. The time passes and you're stuck here. Okay? So there's no motion, no acceleration, and there's no motion, period. Here it looks like the steepness is getting less as you travel in time. So steep, less steep, less steep, less steep, less steep. So you're reaching a plateau, basically. So this looks like as the velocity is decreasing, you are decelerating because you're slowing down, and it's a variable motion. Now this is where you have to be super careful. Now we're changing from a position time to a velocity time. You cannot look at these graphs the same way. They are very different. Okay? This is a velocity time graph. You can see clearly that as the time passes, your velocity increases. I hope everyone sees that. So think about it. As the time passes, your velocity increases, and which means you are accelerating, and it's variable motion. In here, I can see the time passing, but my velocity is stuck at the same number, so constant velocity. And if you notice down here, it was no motion. But if it's a VT graph, that's a constant velocity. And there is no acceleration, because you're not changing your velocity, and this is a uniform motion. This one, you can see that the velocity is dropping. I think you got the idea. You are decelerating, meaning you're slowing down. Not uniform, but variable motion. And here, you're right on the time axis, which means your velocity is 0. So basically, nothing is happening. The object is not moving. Now, we're going to look at the bottom part of this graph, of this page, and we're going to answer the questions. So it says, for each of the axes below, draw the graph corresponding to the description on the left. We might have more than one answer for these problems. It says decelerating. So all I have to do is that I have to show something that has less and less of a slope in time. As the time passes, the slope in the position time gets less. So I can do maybe something like that, right? But it will not be a straight line though. Or it could be something like here in red. Okay? Here it's uniform motion, which means the slope is constant, and the only way you can get that is by doing a line. And it doesn't have to start at 0, by the way, or this. Or it could be any line, it could be under the time axis, right? Okay. Increasing speed, so I have to show something that has an increasing slope in time. So it has to be a curve like this, or the other option is maybe something like that. Anything that gets steeper in time is good. Variable motion, you pretty much have the first one and the third one. So I'm not going to draw that, you got the idea. Any one of those is valid. Okay, let's look at this guy. All right, for number 8, it's giving us a graph, but it's not labeling it. Okay, so it's saying if the vertical axis is position, does the object ever change direction? So if I put position here, I guess I call it X. It looks like the position is starting from high numbers and it's going down to low numbers, right? And then it changes. It starts to go from low to high. So yeah, we are changing direction in this case. So we're going from high to low, then we're going from low to high. And the only way you can do that is by changing direction. Another way you can look at it is the velocity at this point here is 0. The velocities here are negative. The velocities on this side are positive. So you cannot go from the negative numbers to positive numbers without passing through 0. If the vertical axis is is velocity, does the object ever change direction. So if this is a velocity time graph, you do change direction each time you cross the time axis. So yeah, you do change direction at 2 seconds and at 8 seconds. Okay. So just be careful how you read these graphs. Number 9. Okay. These are velocity time graphs. Okay, so we're going to rank this based on the displacement. Now, if you have a velocity time graph, the displacement is just the area between the curve, the line basically, and the time axis, right? So I'm going to look at each box as 1 square unit. So I have 1, 2, 3, 3, 4, 5, so that's a 5, okay? But it's a negative 5, okay, because it's below the time axis. This is going to be, I'm just going to find this area here. So it's, what is that? 1, 2, 3, 4, 5. So what's 1/2? 5 times 1 1/2. Okay? So, and that's going to be a positive number. So what is it going to be? 2.5 times 1.5. Okay, so 375. So this is 375. This one here looks exactly like the one we just talked about now, except that it's negative. Okay. This one here is okay. So it's 1, 2, 3, 4, 5 times. It looks like it's 1 1/2. So that's 7 1/2, and it's positive 7 1/2. This one here, you're going to end up with some negative number here and an equal number but positive on the other side. So this one should give us 0. This one is the area of this triangle here. So it's 1/2. 1, 2, 3, 4, 5 times the height, which is 1. So that should be 2 1/2. Okay. So if we're going to rank them, it's going to be, should be D first. Then comes B. Then comes F, then comes E, and then C, and then A. Okay. Now you just got to be careful here. If it did say the magnitude of displacement, you turn all these negatives into positives, and then you rank them. So just be careful whether it says magnitude or just says displacement. All right. Velocity time graph. Now, this is talking about the distance traveled, so which means we don't care about the negatives. We don't care about which way we're traveling. So if I'm walking 5 steps either right or left, it's still 5 steps. But in terms of displacement, that could be a positive 5 or a negative 5. All right. So basically here, to find the distance, I'm just going to find the displacement for these things here. And turn it into a positive number and add. So this one is going to be positive 5, basically. Okay, well, it's negative 5, but after you change it, it becomes positive 5. This one is going to be 1/2 base, which is 5 times height, which is 1.5. So that's 375 positive. This one is going to give me 375 negative, but in terms of distance, it's positive. This one, I think we did earlier. This is 7.5 positive. This one, you're going to find this area and add this other area to it. And you're going to make both of them positive. So this is going to be half the base, which is 2.5 times the height, which is 1. But I have to add the other piece to it, so it's going to be twice as much. So this is just going to be positive 2.5. That's the distance. This one is going to be half base of 5 times the height of 1, so this is going to be 2.5. So in terms of distance, it looks like D goes first, then comes A, B and C are equal, and then and E and F are equal, and last. 11. I think this one is done in the previous video, but I'll go over it again. So if you throw something up in the air, when it reaches the highest point, it has to change direction and come back down. This velocity time graph is not showing you that it's changing direction. So basically what this is showing you is you throw it up in the air, it slows down, it gets to the highest point, its velocity becomes 0, and it just decides to keep going up at a higher speed. Okay? So a correct way of doing this graph would be that. Okay? So you throw it with a certain speed, let's say up is positive, it starts to slow down. When it gets to the top, its velocity becomes 0 and it changes direction and it comes down the other way. So down is negative, so that's why your velocities are negative. All right, number 12. All right, here again, it doesn't tell us what kind of graph it is, but they keep changing it. So if the vertical axis is position, okay, so if I make this position here, okay, does either child ever change direction? No, they don't. And the reason for that is because position is increasing in both cases. It never kind of like increases and then it decreases. It just keeps going up. Another way you can look at this is that the slope of either one of these lines always remains positive. It never turns into 0 and becomes negative. If the vertical axis is position, are the two children ever at the same position? Yeah, sure, they're going to be at the same position here, which is about 2 seconds, and here, which is about 9 seconds. Okay. If the vertical axis is position, do the two children ever have the same acceleration? The answer to that is no, because Ariel has no acceleration, going at a constant velocity. Byron is constantly changing speed, so there will be an acceleration for Byron, but no acceleration for Ariel. If the vertical axis, if the vertical axis is velocity, do the two children ever change direction? So if this is velocity, they will change direction when they cross the the time axis. So Ariel will do it at 5 seconds, and Byron will do it at 6.5 seconds. If the vertical axis is, if the vertical axis is velocity, do the two children ever have the same velocity? Okay. Yeah, they're going to have the same velocity when their curves intersect. So it's going to be at 2 seconds, and it's going to be at 9 seconds. Okay. If the vertical axis is velocity, do the two children ever have the same acceleration? Okay. I think I skipped C here. Yeah, I'm going to go back to C. Okay. Yeah, let me finish. Actually, I'll go back to C. If the vertical axis is position, do the two children ever have the same speed? Okay. Yeah, they will have the same speed when their curves have the same slope. So if you think about it, if you do the tangent somewhere in here to this curve, okay, that's going to have the same slope as the line for Ariel. Okay. So yeah, they will have the same. You will have the same speed around, I would say, about 6 seconds. All right, now we go back to the G. If the vertical axis is velocity, do the two children ever have the same acceleration? Yes, they do. And basically, in a velocity time graph, the acceleration is given by the slope of the curve. So if I take the slope here, if it's velocity time, that's going to give me the acceleration at this point here. And this line will be parallel to that line, so which means they're going to have the same acceleration. Hello everyone. Today we're going to talk about the graphical analysis of motion graphs. So we're going to talk about position time, velocity time, and acceleration time graphs. And we're going to see how we can go from one to the other. And I want you to understand that all three kind of graphs give you different information. So you have to really be careful about what graph you're looking at. So this is a speed time graph, and we're going to try to use this idea here. So if you have, I'm going to talk a little bit about this. If you have a position time graph and you want to find the velocity, you do the slope. If you have a velocity time graph and you want to find the acceleration, you do the slope. If you have an acceleration time graph, if you do the area between the curve and the time axis, you're not going to get the velocity, you're going to get the change in velocity. And if you have a velocity time graph, and you do the area under the curve, or between the curve and the time axis, you're going to get the change in position, which is just another way of saying displacement. So let's take a look at this. This is a speed time graph, so you got to be careful with that. Now, here it says, what's the acceleration between 4 and 6 seconds? Well, between 4 and 6 seconds, the acceleration is the same as between 4 and 7 and 4 and 8. So all I have to do is find the slope of this segment here. Okay? And the slope of that segment is a rise of 10 and a run of, this is 9, I think. Okay, and this is 4. So it's 10, okay, and a run of 5. So that should be 2 meters per second, which means your velocity is increasing by 2 meters per second every second. Okay, the next thing it says, when is the object traveling with the fastest speed? A lot of people make the mistake and they say, well, it's traveling with the fastest speed in this time interval here, right? So that's between 12 and 15. That would be true if this were a position time graph, but this is a velocity time graph. So with velocity time graph, if you want to figure out your speed, you just read the graph. And your highest values happen to be up here. So it's between 9 and 12 seconds. A lot of people fall for that. All right, so I don't want to scroll, so I'm just going to look at my notes here. At what time is the object not moving? Well, it seems to be that the object is always moving. It will not be moving if it cuts the time axis. In other words, that's where the velocity would be 0. But it's always moving. Okay. A lot of people will say, well, it's not moving up here, down there, and down there. That would be true if this were a position time graph. Okay. When does the object have a constant positive acceleration? You want to find acceleration from a velocity time graph, do the slope. So you just have to figure out which slope is positive. So the slope is positive here, and that's it. So it's between 4 and looks like 9 seconds. Does the object have a constant negative acceleration? The same concept. You have to figure out when is the slope negative, and it's between 12 and 15 seconds. So what's the displacement of the object from 12 to 15 seconds? This is another tricky one. So from 12, I should have erased this. From 12 to 15, you have to find the area of this whole shape. What a lot of people do, they only find the area of that triangle. You have to get yourself all the way down to the time axis, right? So you probably found 22 and a half, but it should be 25 and a half because you probably missed this part here, which is 3 meters per second. 3 meters, sorry. What is the object's velocity at 8 seconds? Again, since this is a velocity time, you just read the graph. It should be 14. If this were a position time, you would have to find the slope of this segment. Because if you want to find the velocity from a position time, you do the slope. What's the meaning of the number 6? It means this number 6 here. This means like when the clock starts, the speed is 6 meters per second. So that's pretty much your initial velocity. All right, the next page. All right, let's look at number 13. The graphs represent the velocity of two toy robots moving in one dimension for a particular time interval. Both graphs have the same time and velocity scales. Is the magnitude of the displacement of the robot in case A greater than, less than, or equal than that of in case B? Okay. So if you want to find the magnitude of displacement, so we have to find the displacement here, turn it into a positive because it says magnitude. Find the displacement here, okay, and add them together. So the displacement here, it just looks like 1/2, 1, 2, 3, 4, base times the height of 3. So that should be just a 6. And this is a 6. Well, this is a -6, but in terms of magnitude, you make it a positive 6. So this is going to give us a positive 12. This one here is going to be 1/2. The base, which is about 2.5, times the height, which is 2. So this is 2.5. This part here is 1/2. The base, which is 1, 2, 3, 4, 5.5. Okay, times 4. It looks like. So it's 2 times 5.5. So that's 11. So 11 and 2.5 is greater than 12. So the magnitude of displacement is greater in case B. Okay, or less in case A. Let's look at number 14. The graphs below show the velocity of two objects during the same time interval, right? So here to find the displacement, we technically just find the areas here. So this is 1/2 base times height, so this is a 1. What we got here? This is a trapezoid, kind of, so you can do the area of the trapezoid. So that should give you about 4 units for the area. In this other trapezoid, it's what is it? 2 plus 4, that's 6. Divided by 2 times 2. So this is a 6, basically, right? So the displacement is greater for object 2. All right, number 15. The graphs below show the position versus time for 6 boats traveling along a narrow channel. Scales on both axes are the same. In each graph, 2 points are marked with dots. Okay. Rank the situation on the basis of displacement. Now, if this is a position time graph, to find the displacement, all you have to do is do the change in position. Okay? You don't do the area. You just got to be careful here. This is not a velocity time graph. This is a position time graph. So now, if you do the change, you do the final, which is 0, minus the initial position, because this comes first. Okay? In here, it should be, I don't know what I did in the answer. Okay, I think I made that 3/4. No, I'm sorry, 1.5. Okay, so this is going to be -1.5 minus -1/4, or 0.25, basically. Yeah, I think that's what I did. In here, this position here is, it looks like it's 1.5 minus half, basically. Okay. In this position here, it looks like that's, I don't know what I did here. I think I made that quarter, basically. So -1/4 minus -half. Okay. In here, this is -1 minus 1. Okay. This is 1. Okay. This here, it looks like it's positive 1.5 minus the initial. It looks like it's what do you call it? 1.75. It looks like. Okay. Yeah, that's what I did. Okay. So you just have to calculate this and rank them, and you have to keep the negatives in there. So the ranking should be B, A, E, and then F, D, C. Okay. So just the only thing you have to be careful here is what kind of graph you're dealing with. This is a position time. To find the displacement, you just do the change in position. Okay? If it says magnitude of displacement, you do the change in position and you drop the negative signs. So now this is a position time. Okay? It has to be looked at differently than a velocity time. Now here it says describe the motion in each of the 3 segments. Of the segments 3 ways. you have to figure out what the direction is, whether you're speeding up, slowing down, or you're going at a constant velocity, and is your acceleration positive or negative. From A to B, you're not going anywhere, right? And that's the same thing from F to G. So let me just show that here. So from A to B, okay, from A to B and from F to G, same motion, right? Are you speeding up, slowing down, or constant velocity? Well, you're not going anywhere. And there is no acceleration. Same thing down here. Okay. From B to C, it says that this is a line, which means your velocity is constant, right? Because in a position time graph, your velocity comes from the slope. So from B to C, you're going at a constant velocity, and you're doing that in the positive direction. You can look at that two ways. Your position is increasing in time, or you can see that the slope is positive. It's a unique slope here. So which means, and the slope is velocity, so you're moving in the positive direction. And you have no acceleration because you're going at a constant velocity. If you look at E to F, is the same idea. So except that here you're moving in the negative direction because your position drops, or you can see that your slope is negative. So this is negative, but you're doing it at a constant velocity with no acceleration. From C to D, you can see that you're still going in the positive direction. Your position is increasing, or you can see that your slope, even though it gets less, it's always positive. So you're going in the positive direction, but it looks like you're slowing down because here's the steepness here, and it gets less and less and less steep. So you're losing speed. Now, think of this as a positive. This is a positive thing. Think of this as a bad thing. So the product of these two is a bad thing. So that's a negative acceleration. And from D to E, you're going in the negative direction. Position is dropping, or the velocity is negative. And the other thing is, your velocity is increasing because your steepness is getting more and more in time. Okay, bad, good, bad. Okay, next video. Next graph. Okay, describe the motion in the 4 parts of the graph below. The scale for time is 1 second for each box, and the scale for distance is 10 meters for each box. So 10 meters for each box here, and 1 for each box here, 1 second for each box. What's the meaning of the d-intercept? Well, this just means that when the clock started, you were at the origin. Now I'm going to try to sketch a velocity time. Now I can see that the slope here is negative. So which means I have to allow some room below the time axis. So velocity, meters per second, the time in seconds. Okay. Here, my velocity is changing. It's increasing in time. So my graph should look something like this. Okay. In here, my velocity is constant, so my graph should be pretty flat. Okay. But the steepness of this line is much less than the steepness here. So there should be a drop here, and then a straight line. And you can put the times in there. The value, this value here, you should be able to calculate that by doing the slope here. So 1, 2, 3, and so it's 30, 2, 4, 6, hold on, can't count. 2, 4, 6, 8, 9 it looks like. So it's 30 over 9, you can figure that out. Okay? And here you're not going anywhere, so it looks like this. And you will have to put the times here. And here it's a negative slope of 2, 3, 4, 50 over 4. So you will have to come here and do negative 50 over 4, which is 12 and a half, down, and just draw a line. That's how you do it. Okay. All right, next page. Chris, make sure we still recording. Okay. Now we're going to analyze this other graph. It says find displacement and acceleration at 2, 6, at those times basically, 2, 6, 12, and 14 seconds. Now this is a velocity time. I'm just going to show the graph and look at my notes. Okay. At 2 seconds, it means between 0 and 2 seconds. If you want to find the displacement from a velocity time graph, which means you want to find the change in position, you do the area between the curve and the time axis in a velocity time graph. So 2 seconds, you have to find this area. 6 seconds, you'll have to find this whole area. We already found this, so you just have to add the area of this house-looking thing. Okay? And at 12 seconds, you just have to add this area and this area. You can see that these two areas are the same, except this one is going to be considered negative, and this one is going to be considered positive. So these pretty much are going to cancel out, which means that your displacement at 12 is the same as your displacement at 6. Now the distance. And then we're going to do at 14, which means you just have to add that last piece. And these two already canceled. The acceleration at 2 seconds, well, that's the same as the acceleration anywhere between 1 and 4 seconds. So you just have to find the slope of this segment. Because you find the acceleration from a velocity time graph by doing the slope. And you can do the same thing for 6, 12, and 14. For 6 is the slope of this segment. That's the same as the slope at 12. It's the same as the slope at 14. What is the v-intercept? Well, the v-intercept is here. It means that initially, when the clock started, you started with 0 meters per second. What's the acceleration when t equals 7.5? So 7.5 kind of falls somewhere here. You just have to find the slope of this segment, which you already found. What is the displacement from 1 to 2.5 seconds? So basically, you have to find the area between 1 and 2.5 seconds. You have to find this area. Now just keep in mind, if you find an area that's above the time axis, it's positive. If you find something that's below, then it's negative. Because here, you're traveling in the negative direction, so your displacement is negative. When is the speed increasing? So this is where we have to be super careful. When you're talking about speed, you ignore the plus and the minus. Okay? So it looks like I'm speeding up here, but I'm also speeding up here between 1 and 4, except that I'm increasing my speed here at a lower rate. Here I'm doing it much faster than I'm doing it here. And then I'm slowing down here, but this is what people forget. You're also speeding up here, you're accelerating here. Because you're going from 0 to 100. You have to look at that as 100, not a negative 100. When is the object moving backwards? This is basically just another way of saying when is the object moving in the negative direction. Well, in a velocity time graph, you're moving in the negative direction if you happen to be below the time axis. In a position time, you will be going in the negative direction if your position drops, okay, in time. Or if your steepness is always, or the slope of the tangent is always negative. Okay. Now we need to make an acceleration time graph here. So I'm going to line it up so I can use the same time scale. And I see that one of the accelerations is negative because acceleration is the slope in a velocity time graph. So I have to leave some room down there. So I have one slope here. I have a different slope up to 4. And then from 4 all the way to 14, pretty much one slope. The slope here is 40 over 1. So here's your 40. This is acceleration, meters per second, or meters per second square. Time in seconds. So at 40, in the first second, it's going to be 40 meters per second. Between 1 and 4, it's 100 over what? No, not 100. 60 over 3, which is 20. Okay? And then
here it's going to be a drop of 200, and it's going to take from 4 to 14, it's going to take 10 seconds to do that. So 200 over 10, that's 20, but it's a negative 20. And this is negative 20. That's that. Pretty simple, right? Okay. Next page. I'm just going to do this page. Maybe I'll skip number 20. So let's just make sure we do this one. And 20 you should be able to figure out on your own. Maybe I'll talk about it just quickly without doing any numbers. Okay. So this one is saying, what's the displacement over the entire trip? But before we do that, let's figure out in what directions we're traveling. This is a velocity time, which means I'm traveling in the positive direction whenever I am above, or whenever the graph is above the time axis. I'm in the negative direction whenever I am below. Okay? If this were a position time graph, you will be traveling in the negative direction each time your position drops. So this is in the negative direction. You'll be going in the positive direction whenever your position increases. That's here. You're not moving here, and then you increase it. You're going in the positive direction. So you just have to be careful how you read these graphs. So the displacement, you just have to find this area, find the area down here between 5 and 25. This has to be looked at as a negative. What time intervals is the object accelerating? Well, you're accelerating when you're speeding up. A positive acceleration does not always mean that you are accelerating. Accelerating means speeding up. So between 0 and 5, you're slowing down. Between 5 and 10, you're speeding up because you're going from 0 to 10. Here you're going from 10 to 5, so you're slowing down. Constant velocity at 5, or constant speed. Here you're slowing down. So each time you're going towards the 0, you're slowing down. When you're going away from the 0, you're speeding up. And what's the acceleration? So what did we say we're speeding up? We're speeding up between 5 and 10, so you just have to find that slope. So it's a drop of 10 and a run of 5. So it's negative 10 over 5. What's the meaning of the y-intercept? It just means like your initial velocity. When the clock started, your initial velocity was 10 meters per second. When is the object moving backwards? That's the same thing as saying when is the object moving in the negative direction. I already addressed that. So it's between 5 and 25 because the curve happens to be below the time axis. When is the object accelerating? We answered that already. Decelerating, meaning like when are you slowing down? Well, you're slowing down here between 0 and 5 seconds because you're going from 10 to 0. Speeding up here because you're going from 0 to 10. Slowing down here because you're going from 10 to 5. Constant velocity here. And you're slowing down here because you're going from 5 to 0. So each time you're approaching the time axis in a velocity time graph, you're slowing down. Each time you're going away from it, you're speeding up. When is the object not moving? We can argue this, but at 5 seconds, think about that. Pause the video and think about what's happening for 5 seconds, and then I'm just going to keep going. So pause it for a few seconds and think about it. At 5 seconds, look, before 5 seconds, the object is moving in the positive direction because you're above the time axis. And here you are moving in the negative direction. The only way you can do that is if you turn around, you change direction. So you have to stop for that split second there and turn. Okay? Now we need to make an acceleration time graph. I see some of the accelerations are negative, some of the slopes are negative, so I have to allow for that. And be careful, not everything is in meters all the time, not everything is in seconds, so you have to just read the problem carefully. Now the slope here is a drop of 20 over 10 seconds, so that's negative 2. Okay? In here, it's a rise of 5, and you do that over 5 seconds, it looks like, right? So that's a positive 1. Or maybe I should label the times. 5, 10, 15, 20, and 25. Okay, so we say this is negative 2. And then and this is a 1. I'm going to try to make it to scale as much as I can. This is a 1. And you're not changing your velocity here, which means no acceleration. So we're taking this line here. And here, the slope is about the same as that. They look pretty parallel to me. Okay? And that's that. So for the next one, I'm just going to talk about it briefly without doing any numbers. If it says what's the displacement for the entire trip, you just find the areas. Anything that's below the time axis, you have to look at it as a negative area. Anything above, you look at it as a positive. Let me just look here. The next one says, what time interval is the object accelerating? In other words, when are you speeding up? Well, it looks like you're speeding up here between 10 and 20, okay? And you're speeding up here because you're going away from the 0. So between, it looks like about, what, 45 and 50 seconds. And you can find the accelerations by doing the slopes. What's the meaning of the y-intercept? You can look at the previous problem. When is the object moving in the negative direction? Each time you're below the time axis, you're moving in the negative direction. When is the object accelerating? We talked about that. When is it decelerating? When is it slowing down? It looks like it's slowing down here in the first 10 seconds because you're going from some number, which is negative 20 to 0, okay, which is basically 20 to 0. And you're slowing down here because you're going from 20 to 0, and that's between about 35-ish, 35 to 45 seconds, okay? But down here, you're speeding up. Okay. What are we? When is the object not moving? It's at 10 and 45 seconds. There's a change in direction. And we make an acceleration time graph. I'm pretty sure you know how to do that. Okay, and we're done. Thank you very much. See you at the next video.
Number 16. And we get to. Okay. So this is a velocity time graph. Okay, so they're making some statements, and we have to see which one is correct. The robust displacement is positive because the slope of the graph is positive. Well, the slope in a velocity time graph does not give you displacement. It gives you acceleration. So Arnold is out. Look at Betty. Now the robust displacement will be 0 since it moves in both the positive and negative direction during this time. It does move in both directions, but it spends most of its time in the negative direction than it does in the positive direction. Okay? Because it's staying a lot longer here than it does over there. So she's out too. I think the displacement is negative since the robot has a negative velocity for a longer time. That's what I just said earlier. So you have a negative velocity for 1, 2, 3, about 4.5 units of time. Here you only have a positive velocity for about 3.5 units of time. For these two graphs, these are velocity time graphs. The students are making these statements. I think object 2 will have the greater displacement because it gets to a higher speed faster than object 1. I'm looking at the right one. I think I mixed this up. I think object 2 will have the greater displacement because it gets to a higher speed faster. Badu says no, object 1 will have the greater displacement because it travels for longer than object 2. I think Andy has the right answer, but for the wrong reason. We can see that object 2 has the larger displacement because the area under the graph is greater. So I think what we need to do here is just find the areas, and which I think we did earlier. So this is 1/2 base times height. That's a 1. I think this is 2. This is trapezoid, so 2 to 5. That's 3 plus 1 is 4. So this is times divided by 2 times 2. So that's 4. So the whole thing here is a positive 5. And here I think we did it earlier. It was a positive 6. Okay? So I think Connor is correct here. Let's look at number 18. Okay. Now this one is talking about distance traveled. Okay, not displacement. So we have to find the displacements and change them into distances. Okay. So what it's given us here is given us from 4 to 6 seconds. It's given us that graph. It says that it covers 6 meters. So from 4 to 6, so what is that? 2 times 3, that's 6, right? Okay, that's the area there. Okay, so all we have to do is find the area between 0 and 2, 2 to 4, and all that stuff, right? So from here, for 0 to 2, it's 1/2 the base times the height. Okay, it's negative, so this is going to be a -3, but in terms of distance, that's a positive 3. So if this is 1, 2, 3, 4, if that's taken 6 bars, this is going to take 3 bars. And you shade that area. Then you do the same thing for this part, which looks like these two triangles are, what do you call them, identical. So we're just going to cover the same amount, same area. This one looks about the same as this one, so it's the same thing here. Okay. This one looks different from E to 10. So let's figure out what that area is. So it's 1/2 the base, which is 2, times the height, which is 2. So it's a 2. So this one is here. Okay. And the next one is this area here, which is 2 times 2, which is a 4. So that's 1, 2, 3, 4 here. And then from 12 to 14, you have to do each area and you have to add them. Okay? In terms of displacement, it looks like it's 0, but in terms of distance, it's something else. So it's 1/2 the base, which is, I'm looking at this little triangle here, basically, which is 1 times the height, which is 2. So that's a 1. And then you have another 1 on top of it there. So that's should be 2 bars in there. Okay. Number 19. For number 19, this is talking about the instantaneous velocity, right? So rank these situations on the basis of velocity at the point indicated. So the velocity here, since this is a position time, is just the slope of that line. Okay, and it doesn't say the magnitude of velocity, so the negatives do matter here. So it's 1, 2, 3, so that's a 3/6, okay? This here is going to be, I'm just going to find the slope of this whole thing. Further apart the points are, the better value you're going to get for the slope. So it's going to be definitely negative, and it's going to be a drop of 2. Yeah. And a run of, it looks like it's 1.5. Okay. So this looks like it's about negative 4/3. This guy here looks like you rise by 2, and it's positive 2, and you run 4. So this is just half. This is also half, positive. This guy here is a rise of 1, and a run of 1, 2, 3, 4, 5, 6, positive. This one here is a drop of 1, so that's a negative, and a run of 6. This guy here, I'm going to go between these two extreme points here, so it's 1, 2. That's a drop of 4, and a run of 3. So let's rank these velocities. So I'm going to get rid of all this extra junk here. Okay. So which one is the highest? It looks like it's A and B. Yeah, this is A and B. Okay. And then comes, so this is done. Then comes E. That's done. Then what else? And then comes F. That's done. And B and C are last. Okay. All right, let's look at number 20. So here we're looking for the average velocity. Okay. Find the average velocity. We just add up the velocities and divide by 2, I guess, right? Because it's a constant acceleration. So this is just going to be you're going from 0 to 2. So it's going to be 2 over. So this is a 1 in here. This is going to be 0. This one is going to be negative 2 plus 0. So this is going to be negative 1. This guy here is going to be 1, positive. This was positive. This one is going to be this value, which is negative 1 plus, so that's going to be 0. And this one here is just going to be, looks like it's also 0. Okay, so to rank this, it's going to be A and E together. Then comes D, C, and F all together. And then the last one should be B. Okay. So your position is positive, so you are to the right. So it's giving you an example here. The velocity is positive, okay? So you're going away from the origin, it looks like, right? Yeah, that's what it means by towards or away. And speeding up or slowing down, you speeding up because your acceleration is positive and you're going to the right. Okay, so we're going to use this idea here. Your acceleration will be positive if you're speeding up in the positive direction. Okay, it can also be positive if you're slowing down in the negative direction. And this will be negative if you're speeding up in the negative direction, or if you're slowing down in the positive direction. So that's how we're going to do this. All right. So here your position is positive, which means you are on the right side. Okay, so I'm going to fill in the positions first. So right, 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 left, 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 left. Okay. The direction, if your velocity is positive, you're going away from. So away. If your velocity is negative, it means you're going left, which means you're going towards the zero here. So here you're starting from the right, and you're going towards the zero. Okay. Here you're starting from the right, and you're going towards the zero also. Right. Here your velocity is positive. Okay. And you are on the left side. Okay. So your velocity is positive, and you are on the left side. So which means you're going towards the zero. In here, you're starting left, you're starting on this side, and the velocity is positive, which means you're also going towards it. If you are on the negative side, and your velocity is negative, which means you're going left, so you're going away from the zero, and same thing for the last one. Okay. All right, let's look at the acceleration. In the first case, the velocity is positive, so you're going this way, okay? And you're going in the positive direction, okay? So your acceleration is positive, you're going to the right, so you must be speeding up. Okay. No, I was looking at the wrong one. So it's already saying speeding up. Okay, your acceleration is negative here, so you're here basically. Your velocity is positive, your position is positive, so you must be slowing down. Okay, I'll fill in the other ones. All right, so in this one here, your acceleration is negative, and you're traveling away from zero, right? Okay. So that's why you're slowing down. Okay? All right. So let me take a look at another one. Okay. Or let's look at this one here. So here your acceleration is positive. Okay. Your velocity is positive, and your position is negative. So let's try that. So you are here. Okay. Yeah, you started here. Your velocity is positive, so which means you're going in that direction, and your acceleration is also positive. Okay. So when the acceleration and velocity are in the same direction, it means you are speeding up. When they're in opposite directions, it means you are slowing down. Okay? And that's it. Basically, you can just look at the product of these two signs here. So positive times a negative is a negative, so which means it's slowing down. This should be slowing down. It should end up giving you a positive, which means you're speeding up. Speeding up. Positive and negative means you're slowing down, and speeding up at the end. So you can just multiply the product of the sign. You can multiply the signs of velocity and acceleration to figure out whether you're speeding up or slowing down. All right, let's look at 22. So we have to rank them based on acceleration. And it does not say magnitude of acceleration, so we're going to keep the negatives in there. So the acceleration here is basically just the slope of these segments here. So it's 2 over 4, so half, positive half. This one, you go from, it's going to be definitely a negative slope. So you go from 2 to negative 2, that's a drop of 4 in 4 seconds. So that's a negative 1. This one here is a rise of 2 in 4 seconds. So it's a positive half. This one is a drop of 2, which is negative 2 in 4 seconds. So negative half. This one here is a drop. It looks like it's 2, so negative 2 in 4 seconds, negative half. And this one here is a rise of positive 2 in 4 seconds. So that's a positive half. So which one has the highest acceleration? It looks like it's A, B, and C are tied for the first place. A, B, C, we'll put a circle around them. Then comes E and F for 4th and 5th place. And it looks like D is last with a negative 1. Okay.
Now here we're just going to describe the acceleration. In other words, is it positive, negative, or 0? In here, this is a straight line, so the acceleration is none. Here, we're going in the positive direction, but we're slowing down. So the acceleration has to be the opposite sign of the direction of travel. Here, we're speeding up, right? But we're doing it in the negative direction, so the acceleration will also be in the negative direction. Here, we're slowing down in the negative direction. So each time you slow down, the direction of the acceleration is opposite the direction of motion. So here it should be positive, and since this is a line, it's 0. Same reason in here. You're going in the negative direction and you're speeding up. So the acceleration will be positive, okay? Because you're going in the negative direction and you're speeding up. So when you're speeding up, no, this is going to be negative. Sorry. Because you're speeding up, it's going to be in the same direction of motion. This is 0, okay? In here, you're speeding up, right, because you're getting steeper, but you're doing that in the positive direction, so your acceleration will be positive. Here you're going in the positive direction, but you're slowing down. So acceleration, the direction of acceleration will be opposite the direction of travel, which means negative, and here this is a line 0. Last one. Okay, we're going in the positive direction, speeding up. The acceleration will be in the same direction as the direction of travel, so it's got to be positive. This is a straight line, this is 0. Now you're going in the negative direction and you're speeding up. So you're going in the negative direction and you're speeding up. So the acceleration is going to be same direction as the direction of motion. 0. We're slowing down, but in the negative direction. So slowing down in the negative direction, this has to be positive. Okay? Because you're going in the negative direction, but you're slowing down. So the acceleration would be going in the opposite direction of the velocity or the direction of travel. There are many ways you can draw this. For a lot of them. For some of them, it's only one way. So basically, you're given a graph, and you have to come up with the other two. I'm not going to do this. The answers will be in the answer key on Haiku. So I'm just going to skip these 2 pages. Actually, there's 3 pages. Okay, and you can look up Haiku and find the answer key. Now, this one we're going to try quickly because we did this in the last unit. This is a velocity time graph. And we're going to do that PVA business. So when you go in to the right, it's slope. When you go in this way, it's area, right? But I'm going to put a delta here. And if you recall, the delta is giving you the changes when you're doing the area. So if you have an acceleration time graph, if you do the area between the curve and the time axis, you don't get v, but you get the change in v. All right. When is the object moving backwards? This means when is the object moving in the negative direction? Okay. So the object is moving in the negative direction whenever the velocity is negative. So that happens between 7 and 10 seconds. What's the significance of the y-intercept? Well, this basically just tells you that when the time starts, when the clock starts, you're moving at 10 meters per second. So that's your initial velocity. When is the object not moving? At 7 seconds, right? It's going to turn around. The object is going to turn around. So it's going in the positive direction up to 7 seconds, and then it turns around and it starts to go in the opposite direction. What's the instantaneous velocity at 3 seconds? All you have to do is read the graph. Don't do any slope. This is a velocity time. Just go up, okay, and come across, and estimate what this number is. And I estimate it to be about 14. What is the final displacement? Find the area. Look at it as a positive. Find the area. Look at it as a negative. And you're pretty much done. So we can do, I'll let you do that. That should be pretty easy. All right, let's look at this problem here. And for the justification or the explanation, I'm just going to talk about it and you can.
Right. Looking at RT1, we're trying to find the magnitude of the change in velocity. So the change in velocity here is 20 minus 10, so that's a positive 10. Here it's negative 10 minus 10, so that's negative 20, but in magnitude, that's a positive 20. And here, 0 minus 10 is negative 10, but it's a positive 10 in magnitude. Same thing here. So C comes first, then A, B, and D come next. Okay. All right. This one here is asking us to find the magnitude of the average velocity over the first 2 seconds. So this is the starting time. So this is 0, 1 second, 2 seconds. So if it's over the first 2 seconds, all we have to do is just figure out the displacement, because we're going to be divided by 2 seconds in all cases. So the displacement here is 4, positive. It's 0, 1, 2, it's a positive 1. 0, 1, 2, that's a positive 6. Be careful here, we started from 1, so it's 1, 2, but there's a difference of 8 in position. So it should be D, C, A, and B. All right, for this RT3, I'm going to start with the velocities. Those are pretty easy to see. So it's 0 here, it's positive, 0, negative, negative, and positive. Because all these points here are below the time axis, and this is a velocity time graph. I'm going to do the acceleration. The acceleration is the slope in a velocity time graph. So it's positive, positive, negative, negative, positive, and negative. The position, since they all start from the same origin, the position is basically going to be the same thing as the displacement up to that point. So the displacement here is negative. Displacement here is positive. Displacement there is positive. Displacement here is going to be negative. Displacement here is negative, and displacement on the other one is positive. All right, let's look at RT4. Okay. The following drawing represents stroke flash photographs of a ball moving in the direction of the arrow. Circles represent the position of the ball. Okay. Rank the magnitude of acceleration. So the magnitude of acceleration can be looked at as the spacing between the balls in time. Okay. So when it's saying magnitude, so we don't care about the direction. I can tell you that C has to come last because there is no acceleration period, and it looks like A and D go first. Spacing is more or maybe Yeah, and it's B and B. Okay, they look identical. And then A comes next. All right, this one, this RT5 is talking about speed. Okay, and it's talking about speed only in the last time interval, right? So we're just going to concentrate on the distance here. The time interval is the same, so you just have to figure out the distance between the last two flashes. So it looks like A and D are first. And they look equal. This distance looks about the same as that to me, at least. And then it looks like B comes next. There's more space in here than in C. Okay. Okay. Now we're going to do RT6. A student makes a statement that the acceleration is 0. Okay. I think that the button has the larger acceleration because the button is at the rest. So it's saying that because the velocity here is 0, the acceleration is also 0. Not true. So think about it this way. If I throw this marker up in the air, it goes up, it stops at the top, and it comes back down. But when it stops at the top, it doesn't mean that gravity is not acting on it anymore, right? So to find the acceleration, you just do the slope in a velocity time graph. So those two graphs, or the acceleration at those 2 points, are exactly the same because those lines have the same slopes. For number 7, this statement is correct because when the cyclist is going up the hill, she decides to just coast up the hill, right? So in other words, she's not pedaling anymore. So the bike is just going to start to slow down at a constant rate. So that's a correct graph. All right? I'll see you later. In this video, we're going to solve some vertical motion problems. Okay. An object is number 19. An object is shot up in the air with a speed of 80 meters per second. So that's your initial velocity. How many seconds will it rise? Okay. So for part A, the initial velocity is 80, positive 80. So we're going to look at up as positive. The final velocity is 0. That's the highest point. The acceleration is negative 10 meters per second squared. Gravity is always bringing it down in the negative direction. And find the time. Let me just write the equations here first. Vf is Vo plus AT. Vf squared is V initial squared plus 2A, which is basically negative 10. Delta x, so I'm going to call it delta y since it's in the y direction. Delta y is Vo plus Vf over 2 times t. And the last one is, delta y is Vot plus half times negative 10. So for this one, I think I'm just going to use Vf equals Vo plus AT. Basically, this is 0. And conceptually, you should know that it's going to take 8 seconds to get up to the top without doing the math, because every second, you're going to lose 10 meters per second. So it's going to take you 8 seconds to lose all of your 80. Here's the math that goes with that. Okay. Be careful with the algebra here. This is not 70. So t is equal to 8 seconds. How many seconds will it fall? Well, the time it takes to go up is the same as the time it takes to come back down, so it's 8 seconds. How far will it fall? So basically, how about if we figure out how high it will rise first, okay? Before we figure out how low it will fall. So we're looking at, I guess I can do D first, or I can do C. I can show you how we can do C also before D. So how high does it go? So the initial velocity is 80, the final is 0. You have the acceleration, you have the time. So I think you just pick the simplest of all the equations. I think I'll use the third one here. So it's VO is 80 plus 0 over 2 times 8. That should be 320 meters. Let me just double check that. Yeah, 320. Now, if we do it from the top down, the V initial is 0, the V final is negative 80, and the time and the acceleration is negative 10, the time is 8 seconds. Okay? So if you do the math here, you're going to end up with negative 320, which means it dropped 320 from the starting place. Okay. How high is it at 3 seconds? So the initial is, we're looking at part B, 80 meters per second. The final is not 0 because we're doing this at 3 seconds. The acceleration is negative 10. Okay, and we're just trying to find the delta y, the time. So it's going to be VOT plus 1/2 a t squared. And if we do the math here, we should end up with 195 meters, positive 195 meters. So 95 meters above what you started. At what time, times, okay, is it at 275 above the ground? So you're going to hit that position twice, once on the way up and once on the way down. So you have to find two values for time, which means the logical equation to use is the very last one here that has the time squared. That's a quadratic that's going to give you 2 times. So 275, after writing the equation, of course, positive 275 equals 80 times t minus 5 times t squared. And if you solve that equation, you should get your 2 values for t. So I didn't do it, so I'm going to do it here. You can do it on the calculator, actually. So I'm going to graph it. 275 minus 80x plus 5x squared. I'm going to graph that. So we get 5 seconds, and the other one is 11 seconds. So it means you could have probably factored this. What's the acceleration and velocity at the top? Well, the acceleration at the top is negative 10 meters per second squared. Either way, on the way up or down, so it's always there. And the velocity at the top is 0 because you have to start to change direction. Look at number 20. An arrow is shot in the air at a speed of 50 meters per second, so that's your initial velocity. How many seconds will it rise? Now, conceptually, you should see that it takes 5 seconds for it to get up to the top. Okay? So now let's do the math. Vf equals Vo plus AT. This is 0 at the top. Equals 50 minus 10t. And just like we predicted, it takes 5 seconds up. It's also going to take 5 seconds down. How far will it fall? How high will it go to have fallen that far? So I can do C, and C and D are the same thing. So I can do the delta y equals VO plus VF over 2 times t. Now looking at it from the top, the initial velocity is 0. The final is 50 but negative. Okay, so 0 plus negative 50 over 2 times 5. And that should be, I think, 125. Yeah. That's a negative 125 meters because it dropped from the, what do you call it? It dropped from the origin, which is at the top. How high is it at 2 seconds? We do delta y equals VO. Actually, this one is not going to work because we don't know how, well, we kind of like know how fast it's going at 2 seconds. It's got to be going at 30. I mean, there's a lot of equations you can use here. So maybe I'll just use, what is the easiest? I can use the last one here, times square. So it's 50 times t minus 5 times t squared. So that's 100, and this is what? So that should be 80 meters. I think so. So 5 times 4 is 20. Take that away from 100. Yeah. Take that away from 100. That's 80. At what times is it 150 above the ground? So I think we have to use the one that has the quadratic. So delta y equals VOT plus half AT squared. This is positive 1 and 5 equals 50 t minus 5 t squared. And we solve for the time, and we should get 2 values. So I'm going to try that quickly. 1 and 5 minus 50. So I'm going to graph that. Second trace, 0. So one of them is 7. And the other one is 3. 7 seconds and 3 seconds. That's number 20. Yep, 3 and 7 seconds. Okay. All right, let's look at 21. Now, 21 talks about distances in feet and the velocities in feet per second. So I'm going to change feet per second to meters per second. So this is 29.27 meters per second. 80 feet is 24.39 meters. In other words, we're going to use 1 meter is about 3.28 feet. That's how we're going to do it. How many seconds would it rise? It looks like it's going to be about 3 seconds because you're losing 10 out of 29.27 every second. So let's do the math here. So at the top, this is 0. This is 29.27 minus 10 times t. So this is going to be 2.93 seconds. Good. How far will it rise? So we're going to find delta y equals, I think I'm going to use this one before last because I know my initial speed. This is after your right formula. My final speed is 0 over 2, and it took 2.93 seconds to do that. Okay. So 2.93 divided by 2 times 29.27. So it's 42.88. Just make sure. Okay. 42.88 meters. Slightly different than the answer here on high but that's close. How high is it at 2 seconds? At 2 seconds, I'm going to use the one that has the time squared. So I'm going to write delta y is VOT is half at squared. So it's going to be 29, 27 times 2 minus 5 times 2 squared. So 29.27 times 2 minus 20. So this is 38, 54 years. And what times is it at 24.39 years? So I'm going to use the quadratic. Delta y, I'm not going to write it down. So I'm going to use the same one here. So it's going to be positive 24.39 equals 50t minus 5t squared. Not 50, but 29.27. And I'm going to put that in the calculator. Let's solve it. 24.39 minus 29.27x plus 5x squared. I'm going to find the zero on the calculator. So the first one is 4.85 seconds. Second one is 1 second. Just make sure. Yep. Okay. All right, let's look at number 22. A rocket is fired into the air at 224 feet per second. So we have to change this feet per second to meters per second. So that should be 68.29. Meters per second. Okay. How many seconds will it rise? So we know it should be about 7 seconds. So I'm going to do VF equals V initial plus AT. This is 0. This is 68.29 minus 10t. So t is equal to 6.83 seconds. How high will it go? So I think we can just do delta y. VO plus VF over 2 times T. So this is going to be 68.29 plus 0 over 2 times 6.83. So the delta y equal to 68.29 divided by 2 times 6.83. 233.21. Yes. Okay. Look at 23. I wish to shoot an object into the air such that it will rise 80 meters. So that's my delta y. How long will it have to rise to get to this height? So we're looking for time. Okay. So we have to do it. See, all these equations have the initial velocity in them. So the way I'm going to do this is that I'm going to do it from the top down. Okay? Because the time it takes to get up to the top is the time it takes to come back down. So if I'm looking at it from the top, the initial velocity is 0. And then I will just use we'll use this equation here. So I would say delta y equals dot plus half at squared. Yeah. And this 80 becomes negative 80. This is gone. This is negative 5 times t squared. t should be equal to 4 seconds. So if you do it from the top down, you have to look at that 80 as a negative 80. How fast? Yeah. If you want to look at it the other way, you have to find the initial speed first, but we're not going to bother with that. How fast would it have to be going when launched? Well, we have to do it anyway. So I'm going to find the initial velocity. Yeah. Vf equals VO plus AT. This is 0 at the top. This is VO minus 10 times 4. So VO should be 40 meters per second. And you could do that conceptually. It took 4 seconds to get up to the top. It means you had to fight it with 40 meters per second because every second you're losing 10 out of the 40. 24. An object must be shot in the air so that it rises 405 meters. How long will it take to reach this height? How fast must it be going at launch? So I'm going to do B first, and then I do A. It doesn't matter. So I'm going to try to figure out how fast, what's the initial velocity. So delta Y is this much. Okay. The final velocity is 0. It's the highest point. And I have the acceleration. So I think I'm going to use this equation. Okay, so at the top, this is 0. This is V initial square minus 20 times 405. So VO is equal to plus or minus plus or minus 90 years. But since we're looking at up as positive, we're going to drop the negative. Okay, now I'm going to answer. This was B. I'm going to answer A. How long will it take to reach this height? Well, it should take 9 seconds because I'm going to lose 10 meters per second every second. So it's going to take me 9 seconds to lose everything. So here's the math that confirms that prediction. So 0 equals 90 minus 10t. So you can see that t is going to be equal to 9 seconds. Right. Another one that has feet in it. So we're going to change that to meters. So it's 175, 161 meters in 576 feet. How long will it have to rise to get to this height? So same as before. So I'm going to do A first. So I'm going to look at it from the top down. So the initial velocity is 0, and I'm going to work with the one that has the time square. So I'm going to say negative 175.61 equals, the initial velocity is 0 if I'm looking at it from the top down. That term is gone. Equals negative 5 t squared. So 175.61 divided by 5. We'll take the radical of that. So it should be about 5.92. Let me just look at the answer here. 5.93. Okay, 5.93. 5.93 seconds. How fast must it be going? It should be 59.3, just conceptually, but we can do the math. Now this is 0. So we don't know this initial velocity. And the math should give us 59.3 meters per second for the initial velocity. 26. An object is shot in such a way that it stays in the air 14 seconds. How long does it fall down? Total time is 14 seconds. So it takes 7 up and 7 down. With what speed was it launched? You can can see clearly that it's going to be 70 meters per second conceptually. You can explain that conceptually. If not, here is your map. At the top, this is 0. VO minus 10 times T, which is 7. So VO is equal to 70 meters per second. A ball is thrown into the air in such a way that it returns to your hand 4 seconds later, which means 2 up and 2 down. With what speed did you throw it into the air? 20 meters per second. So it's going to take you 2 seconds to lose all of your 20. Because you're losing your velocity at a rate of 10 meters per second every second. The math is just VF equals VO plus 18. This is 0. Minus 10 times 2, so that should be 20 meters per second. 28, a toy rocket is fired straight up with a speed of 30 meters per second. So that's my initial speed. How long does it take the rocket to reach the highest point? Now it's going to take 3 seconds. Okay, now let's see if the math confirms that. It's going to take 3 seconds to lose 30 meters per second at a rate of losing 10 meters per second every second. This is 0. 30 minus 10 times t. T is equal to 3 seconds. How long is it in the air? Time up equals time down. So for B, I mean, it's going to be 6 seconds. How high does it reach? Okay. We can look at it, how high does it reach or how low does it fall, either way. It's like dropping it from the top. So I'm going to do it from the top down. I think it's easier. Delta y equals 1/2 at squared. Because the initial velocity at the top is 0. So delta y equals -5 times 3 squared. You have to use 3, not 6. So this is -45 meters. So which means it rises 45 meters and it drops 45 meters. That's basically why the negative is there. Okay? So to answer how high it reaches, you just have to say 45 meters. D. With what velocity does it hit the ground? Well, if you fire it with 30, it's going to come back and hit with 30, but in the negative direction. So the velocity should be just -30 meters per second. So it's the same speed with a change in direction. How fast is it going? After 1.2 seconds or at 1.2 seconds. So VF equals VL plus A T. Now T is 1.2 seconds. Now you should know that this velocity should be positive because you haven't reached the top yet. At 1.2 seconds, it's still climbing. So that's going to be, it looks like 30 minus 12, so that's 18 meters per second. At 4 seconds, that should be negative because you pass 3 seconds to get up to the top. So now you're on your way down. So 30 minus 10 times 4 equals -10 meters per second. What is the change in velocity every second on the way up? That should be -10 meters per second every second. That's basically the definition of acceleration. Same thing on the way down. What's the acceleration at the top? -10 meters per second squared. Just because it stops at the top does not mean that the acceleration is 0. When is the rocket? 22 meters above the starting position. So now, it's going to hit the 22 meters twice. Once on the way up and once on the way down. So we have to use the equation that has the time squared in it. So I'm going to use this equation. So it's positive 22 equals 30 t minus 5 t squared. Now, if we put this in the calculator, okay, so here we go. So 22 minus 30x plus 5x x squared. We'll graph that. Second tree, so we're going to find the zeros. Okay, one of the times is 5.14 seconds, and the other one is going to be 186 seconds. Okay, so whenever it says times or certain distance above the launch point, you have to use that equation that's quadratic with the time. All right, let's look at this RT11. So the mass is not going to matter, okay? And yeah, so none of the equations talks about mass here. The maximum height basically is just going to be based on the initial speed. So the first one is B because you fire in it the fastest. Then comes A. The C and D are fired with the same speed. So you will reach the same height. Right. 29. On the moon, an object accelerates at a rate of 1.52 meters per second squared. If a feather was dropped on the moon and fell for 3 seconds, fine. How far the feather fell. Okay, so we have the acceleration. We started with an initial velocity of 0, and we have the time. So we have to use an equation that does not have final velocity in it. So I'm going to use this one. Okay, and I expect this to be negative because we're going below where we started. So this is 0. We drop in it. It says drop. Equals 1/2 times negative 1.52 times 3 squared. So I have 6.84. Just confirm that. Yeah, 6.84. So negative 6.84. The negative just indicates that you're below where you started. How fast was the feather moving after 3 seconds? So you're just going to do VF equals VO plus AT. The VO is 0. The acceleration is negative 1.52 times time, which is 3. So if we do the math here, 1.52 times 3, so it's negative 4.56 meters per second. So in terms of velocity, you keep the negative. It says how fast, drop the negative, and it should be just 4.56 meters per second. And yep, that's what I have here. Okay, number 30. A 70 kilogram physics student is dropped from rest on planet X. So the initial velocity is 0. It fell 4 meters in 1 second. So we have to look at that 4 as a negative. What's the acceleration of gravity on planet X? So we're going to use delta y is VOT plus half AT squared. So this is negative 4 equals, it will drop to VO is 0 equals 1/2 A and 1 squared. So the acceleration is negative 8 meters per second. Okay, for number 31, it says that a 1 kilogram stone was dropped from a building 200 meters high. The 1 kilogram has to go because we're assuming that this is happening. This is a free fall, so which means the mass of the object doesn't matter. It's a 5 kilogram brick, it shouldn't matter, right? The brick was thrown straight down, so you're throwing it down with a speed of 25 meters per second. So in terms of velocity, if we look at it up as positive, that should be a negative 25. Okay. Will the brick ever pass the stone? So the way we're going to treat this is we're going to assume that the brick passes the stone, right? And figure out how long it's going to take before it passes it, and then figure out the time it takes for each to hit the ground. And if the time that they meet is less than the time it takes them to hit the ground, then the brick must have passed the stone. I hope we can see that. Let me repeat that. We're going to assume that the brick passes the stone, and we find that time. Okay. Once we find that time, we figure out how long it's going to take the stone and the brick to hit the ground. So if the time that we find for them to hit the ground is greater than the time it takes for them to meet, then they must have met. If not, then they never meet. In other words, they hit the ground before meeting. Okay. So let's try that. So if we assume that the brick will pass it, so we're going to say, well, the position of well, I'm going to write this as y, I guess, since it's in y direction. Position of the brick is equal to the position of the stone. Okay. So now let's look at the position of the stone, and I'm going to use this equation here. Delta y is v0 t plus half a t squared. So basically, it's going to be delta y equals v0 t minus 5t squared. Now let's say the clock starts when the stone is dropped, okay? Because the time is different. Because you have to wait 2 seconds before you throw down the brick. Okay, so for the stone, it was dropped from rest, so it's just going to be negative 5t squared. Now for the brick, the v0 is negative 25, okay? And it was thrown 2 seconds later, which means it's 2 seconds, it takes 2 seconds less than the stone. In other words, the stone has been in the air 2 seconds longer, or the brick has been in the air 2 seconds less. Okay, minus 5t minus 2 squared. Now, you can put this in the calculator, okay? Or we can actually, it's quadratic equation. Let me try it with the, so minus 25t plus 50 minus, so this is going to be 5. That's going to give me t squared. That's going to be 4t times negative 5, so that's 20t. That's going to be positive 4 times negative 5, so that's minus 20. So let's see what we can do here. Negative 25 and 20, that's negative 5 on this side, so it comes to this side as 5. 50 minus 20 is 30. So the time is 6 seconds. So it's going to take 6 seconds for them to meet, assuming that the brick passes the stone. Now, let's figure out how long it's going to take each one of them to get to the ground. Alright, so for the stone to hit the ground, it's going to be negative 200. I'm using this equation again. Equals negative 5t squared. So the t is going to be is the square root of 40, it looks like 6.324. 32 seconds. Now, for the brick, it's going to be negative 200 equals it's going to be negative 25. I can do t and then add 2 seconds. Yeah, I can do t. I'm just looking for the time it takes the brick to get to the bottom. Minus 5t squared. Okay, so if I solve this equation, actually, let me see if I can do it at the calculator. So it's going to be, I'm going to move this over. I'm going to actually make this 40 5 and make this a 1. Move this here. So t squared plus 5t minus 40, yeah, equals 0. So we put that in the calculator. Let's see what we get. X squared plus 5x minus 40. I'm going to graph that. Okay. Second trace. We find the zeros. I got 4.30 seconds. So it's 4.30 seconds for it to hit the ground, but if the clock started when I first dropped the stone, I have to add an additional 2 seconds because this was thrown 2 seconds later. So this is going to take 6.30 seconds. So now t is less than 6.3 or 32, so which means the brick did pass the stone. If so, when? Well, it did it at 6 seconds. And where? All we have to do for where is just plug in 6 seconds into one of these equations. And I think it's easier to just put it here. Okay? So it's just going to be, that's the position of the stone, which happens to be the same as the position for the brick. So it's negative 5 times 6 squared, and you can do the math. So that's negative 180 meters. So it's 20 meters above the ground. If you want to do it with the other one, you get negative 25. That's going to be 4 minus 5 times 4 squared. So this is negative 100 minus, now that's 80. So that's going to give you negative 180 meters from the dropped spot. Okay. Number 32. A kangaroo jumps to a vertical height of 2.7 meters. How long was it in the air before returning to Earth? So I think the way to do this, I think since we don't have the initial velocity, I think it's better to look at it from the top down. Unless if you want to use an equation and find the initial velocity, which you could. You can do the equation that has no time in it, v squared. Basically at the top, vf squared is 0. You have the acceleration, you have the displacement. You can find the initial velocity and then use it to find the time. But I'm not going to do that. I'm just going to look at it from the top down because of the symmetry. Whatever happens on the way up happens on the way down. It's just opposite in signs, in direction. So I'm going to do, let me see, which one is easier? I'm going to do the one that doesn't have time, that doesn't have VF in it. So I'm going to do this one. Okay. All right, so this is going to be negative 2.7 equals, now we drop in it, we're looking at it from the top down, so it gets to the top and it starts from rest. It equals negative 5t squared. And if we do the math here, we should get 0.735, so 0.74 seconds. Now, that's only on the way down. On the way up, it takes the same amount of time, so you double that and you get 1.47, 1.48 seconds. Okay. Number 33, I'm going to do it a little differently than the way I have it on haiku. A ball player catches a ball 3.3 seconds after throwing it vertically upward. So in other words, the up and down is 3.3. So what we can do here, we can break the motion into 2 halves. So we can just look at it on the way up or on the way down and figure out the initial velocity, right? Because we know the time up, we know the velocity at the top is 0. We can solve it that way. If you don't want to do it that way, you can do this. Try this approach. Okay. Now, if you throw it upwards with the velocity VO, when it comes back to ground, it has a velocity negative VO because speed up and speed down are equal. Now, just make sure the recording is still going. Oh, we're good. Okay. Equals VO minus 10 times T. Now the T is 3.3. Okay, so this is going to be negative 2 VO equals negative 33. And you just divide and you should get 16 and a half, it looks like. Okay. At what height did it reach? Well, so VO here is 16 and a half meters per second. How high did it reach? I think we can just do, which one? We can probably do delta Y equals VO plus VF over 2 times T. VF at the top is 0, VO is 16 and a half. Now, keep in mind that we cannot use 3.3 seconds because we're only looking at it on the way up because we made the VF 0. So this is going to be 3.3 divided by 2. We take half of the time. And you should get an answer of 13.61. Okay. A helicopter is ascending vertically with a speed of 5.5. So it's going up. So this is a positive. VO is positive. At a height 105 meters above the ground. So the ground is at negative 105. A package is dropped from a window. How much time does it take the package to reach the ground? So I'm going to do delta Y equals VOT plus 1/2 a T squared. Now, the 105 is below where we started, so that's going to be a negative 105. It's a negative displacement equals 5.5 T minus 5 T squared. Now we can solve this equation in the calculator, or you can do a quadratic formula, and you should get 5.17 seconds. Okay. Now, for number 35, all the formulas that we talked about, like the 4 formulas that I gave you, when we talk about delta x or delta y, these are displacements. They are not distances. Okay? So just keep that in mind because that's going to be important here. A stone is thrown vertically upward with a speed of 12 meters per second. Okay, so that's the initial velocity. From the edge of a cliff 27 meters high. So your delta y is negative 75 because where it's going to land is below where you started. Okay. Now we don't care about what's happening on this part here because all we care about is the difference between the final position and the initial position. Okay. So if this is 0, anything below here is negative, so it's going to be negative 75 minus 0 basically. Okay. So how much later does it reach the bottom of the cliff? Based on what we have here, I think our only option is this equation here, the one that has the time squared. So we put negative 105, negative 75. Still stuck with the other problem. Equals 12t minus 5t squared. And you should get a negative time and a positive time. So you keep the positive, obviously. 5.25 seconds. So we really don't care about like what happens on this part here. Okay, that's already included in the delta y. The delta y is the displacement. How you get to the bottom is not important. Okay. Some people will try to figure out the time it takes to get to the top, take the time it takes to get to the bottom, take the time it takes to go from here back down here, and add them up together. You can do that, but it's tricky and it's not necessary. So if you want to find the time it takes to get to the top, you can use VF is 0, you can have VI is 12. You can figure out this time, you double it to get here. But here's the tricky part. When the stone is here, it's not starting from rest. So your initial velocity at this point is 12, but negative 12. Because now it's going on the way down. So it can be tricky. So just be careful when you're dealing with this type of problems. I'm not saying you cannot do it, but why do it when you have something as simple as that? Okay. What is the speed just before hitting the ground? So I think we're just going to do VF is VO plus AT. Now this is going to be 12 minus 10 times 5.25 12 minus 52.5. And what is that? That's like 40, negative 40 and a half meters per second. Okay, and it's negative because it's going to hit on the way down. So in terms of speed, it's just positive 40.50. Okay, what total distance did it travel? Now this is different. So if you want to find the total distance, you have to find this distance to get up to the top, double it on the way down, and add 75 to it. So I think let's figure out the distance it takes to get just to the top. Okay, so to do that, I don't know how long it takes to get up here. I could probably figure out how long it takes to get up there, but I'm going to use an equation that doesn't have time in it. So I'm going to use this one. And this delta y is basically not the whole delta y, but it's just like this height here. Okay. So at the top, this is 0. This is 12 squared minus 20 delta y. So delta y is equal, this is delta y, this part here. Okay, so that's going to be, okay, 144 divided by 20, probably do that mentally. I don't feel like it. So 7.2. So it's going to be, the distance is going to be 7.2 to get up to the top, another 7.2 to get down here, and add 75. So times 2 plus 75. So 89.4 meters for the total distance. Now RT12. So a student makes a prediction, makes a statement. So they say faster thing takes less time. That's true. So if he says if I throw the ball faster, it will reach its highest point in less time. Well, yeah, faster things take less time for a fixed distance, for a constant distance. But here, if you throw faster, you're also going to go higher. So it will take longer to get to the top. Okay, so that's what you have to be careful with. Faster things takes less time for a constant distance. Okay. For this problem here, we're trying to figure out how high above here we throw, or we drop. So I'm going to call this H, I guess. Okay. So now the way we're going to treat this is we're going to find the initial velocity for this part when the stone is clearing the window, and that's going to become the final velocity for this part. That's the trick. So for this part here, delta y is negative 2.2 because we're starting from here and we're landing here. Now I don't know this speed here, so I don't know the final velocity. So I'm going to use the equation that doesn't talk about the final velocity, and I'm going to call this delta y basically. VOT. Now the VO is the speed that the marble or a stone is going to have when it's at this level here, plus 1/2 t squared. So delta y is going to be negative 2.2 equals. Now we don't know this VO. Now the time is 0.3 seconds minus 5 times 0.3 squared, which I think we can do easily. So I'm going to try negative 2.2 plus 5 times 0.3 squared. We divide that by 0.3. And we should get negative 5.83. And it makes sense that it's negative because it's on the way down. So that velocity becomes the final velocity for this part here. So for that part, I'm going to do VF squared equals VO squared plus 2a delta y, or I think in this case I call it h. Now, the initial velocity is 0 up here. This VO is not the same as this VO. This VF is this VO. So I hope you can see that. So you have to keep the negative. But you square it and it becomes positive. But you still have to keep it. Negative 20h. So I'm going to take whatever I get in the calculator, I'm going to square it, and I'm going to divide it by negative 20. So I get negative 1.7. So basically it just means that you dropped 1.7 meters from where you started to the top of the window. So the height above the window is 1.7 meters, a positive. Okay, number 37. Planet X has 3 times the free fall acceleration of Earth. A ball is thrown vertically upward with the same initial velocity on Earth and on X. How does the maximum height reached by the ball on X compare to the maximum height? Blah, blah, blah. Okay. Now we're going to do VF squared equals VO squared plus 2A delta Y, I guess, right? Let's get warm in here. Now this final velocity is 0. Okay, so I'm going to find this delta y. But actually, you know what? I'll call it h. Yeah. So h, if I rework this equation, is going to look like that. Okay. Now, they're telling me that the initial velocity. Okay, let me try. I'll show you this maybe ways. Okay, let me do it like quickly, and then I'll show you the long way. So h is negative v squared over 2a. So it's the VO is constant because it says the same initial velocity. So which means h and a are inversely related, right? Which means if planet X has 3 times the free fall acceleration, the h will be 1/3 as much as on Earth. Now, if you don't see that, you can try this. H on Earth equals negative VO squared over 2a. Now, the a is basically our negative 10. H on planet X is equal to negative VO, same initial velocity, over 2a, this is on Earth, on X. Okay, now, this a on X is basically going to be a on Earth divided by 3, so I can just slide that 3 here. Now, if you look at this stuff here, that's basically the h on Earth. Okay? Okay. Hold on a second. No. The 3 is here. What am I doing? The 3 is here. Yeah. So basically, it comes out here and becomes a third. Okay, so this is 1/3 of h cubed. That's what it is. So let's make that correction. A ball is thrown vertically upward on planet with 3 times the initial velocity. How does the maximum height reached by the ball on planet X compare to the maximum height on Earth? Okay, so I'm going to try it. Okay, try it this way here. So if the VO is 3 times, so the VO squared becomes 9 times. So now I introduced a factor of 9. Okay, and the acceleration is 3 times. So now I introduce a factor of 3 here. Okay, so basically I introduced a factor of positive 3. So which means the height on this other planet, X, is 3 times the height on Earth. Now, if you can't see that, h on X equals negative 3 VO squared over 2 times 3a on Earth. That's what it means. Okay. Now I can see that a 9 will come out of here, and the 3 will come out of here, and then I'm left with this. This is all algebra, guys. And this expression here that I'm circling is the same as that. So that's basically h on Earth. So it's going to be 3 times the height reached on Earth. Okay. Number 38 to 43. This is all multiple choice. So the ball is thrown up, it will go up and then come back down. The ball's acceleration during its flight never changes direction. Its change of direction is 0 throughout. It never changes direction, so the answer is A. because gravity is always pulling you down. So you're basically slowing down on the way up and speeding up on the way down. So the acceleration is always down. Okay. The ball's velocity during its flight, it does change direction. Okay. Initial, in the beginning, on the way up, the velocity is upward, becomes 0 at the top, and it becomes negative on the way down. At the peak of the ball's flight, the ball's acceleration is downward. It's never 0. Okay, the velocity is 0, right? But not the acceleration. Gravity never takes a vacation. It's constantly working. At the peak of the ball's flight, the ball's velocity is 0. That's true because it has to stop before it can come back down. You cannot just change direction without stopping. Okay. As the ball travels upward, the velocity is upward, that's true. And the acceleration is downward, that's true. Because it's slowing down on the way up, and gravity is pulling it down. So the answer to 42 is A. I don't need to read the rest. At the instant right before the ball hits the ground, the ball's velocity is downward. I mean, it's obvious. It's traveling on the way down. Okay. Almost done. All right. Planet Dweeb has 3 times the gravitational acceleration of Earth. Okay. So I'm going to write that. A Dweeb is equal to A 3 times. Okay, so basically that's going to be negative 30 meters per second squared. A ball is dropped, so starting from rest, from the same height on both Earth and Dweeb. How much faster will the ball be going when it hits the ground on Dweeb than on Earth? So we cannot use an equation that has time, and because the reason for that, because the time will be different. So the time is not a constant for both of them. So I'm going to use the one that doesn't have time. Vf squared equals VL squared plus 2A delta y, I guess, right? Now, we're starting from rest, okay? So we're trying to find this Vf. So that's going to be 2A delta y with a radical. Since it's going down, it's negative, okay? Since it's saying how much faster, we don't care about that. Negative, okay. Now, the delta y is constant. 2 is a constant. So for the Vf on Earth, that's just going to be, I'm just going to drop the negative. It's 2A on Earth times delta y. The Vf on this planet Dweeb is 2 times 3 acceleration of gravity of Earth times delta y, which is the same. So I can take this 3 here, okay, and bring it to the outside. So it's going to be 3 radical 2A on Earth delta y, and this expression here is basically just the final velocity on Earth, okay, with a radical here, of course. It's not a 3, it's a radical 3. Okay, so now it's going to be radical 3 times faster. So radical 3 is about 1.73, so it's about 1.7 times faster. How much more time will the ball take to hit the ground on Earth than on Dweeb? So in order to do that, we're going to try this maybe. Okay. I'm going to say, well, Vf equals Vo plus A times T. Starting from rest. Now the Vf is going to be radical 3. This is on Dweeb. The Vf on Earth equals what I can actually I can solve for time first. Yeah, I can do that. Let's try it here. So basically, T is going to be, I think we just say that it's going to be radical 3 Vf on Earth over, I think the acceleration was 3 times the acceleration on Earth. Okay. This expression here is basically the time that it takes to fall on planet Earth. So T is going to be radical 3 over 3 times T on Earth. Okay? So So which means if you want to do t on Earth, basically, so t Earth is going to be 3 over radical 3 t on dweeb, which becomes radical 3 t on dweeb, which means 1.7 times longer. Okay. Okay, so now we're given some velocity time graphs, and we have to come up with some speed time graphs. Now I'm going to tell you the explanation as I talk about it, so I'm not going to write anything down. Okay. The speed is basically a scalar quantity, so you can never have a negative speed. Velocities are vectors, so they can have directions, but speeds don't. Okay. So the speed that goes with this is basically just take the absolute value of that, and you should get something like this. Here, you take the absolute value of that, you should get the same thing, just like that. In here, you take the absolute value of that, so be careful how you do this. This comes up here, and this stays there. So it should look something like that. This one, no change, because that's already positive, right? This one here, you have to take the absolute value of this piece, so which means this comes up here, right, like that, go here, and you go here. It's like a V. This one here, no change. Okay? Because speed is a scalar quantity. A student considers these two graphs because they make a statement. States, object 1 will be further from its starting point after the 6-second time interval because object 1 has a larger displacement. Now, displacement does not mean displacement and distance are different, right? So now you can travel a lot of distance but end up with 0 displacement. So a speed time graph, okay, does not give you the area in there does not give you the displacement. Okay, so we cannot say. And the reason for that, because we don't know what the velocity time graph looks like, okay? Because this could be down here, or it could still be up there in the velocity time graph. We have no idea about the velocity time graph, so we cannot tell, okay? Okay. Because with this one here, you might end up with nothing actually, 0. Because this is down here. So you end up with a distance of 0. Actually, you end up with a displacement of 0, right? Okay? Yeah, okay. I think you got the point. Okay, now let's look at the last page. All right, so we're going to talk about the relative velocity here. So the train is going to the right at 24. This person is going to the left at 8. Now, for someone on the outside, like standing on the side, not on the train, what they're going to see, that this person is moving at 16, positive 16. So I think you can imagine that. Here, the train is moving to the right at 20, and the person is moving to the right at 12. So they're going to see this person is moving at 32 meters per second. In here, train is going to the left at 30, person is going to the right at 10. So for this person, the person outside, they're going to see that this person up here on the train is going to appear as if they're going backwards. So that's why it's negative 20. And here, everything's going to appear to be going backwards. So I can say that this is negative 20 meters per second. So now in terms of speed, we're going to drop the negatives. All right, so let's see which one is highest. So it's got to be C, then B, and D come next, and then A is last. All right, and here's the last one. So they're giving us scenarios, and they're giving us a spaceship, it looks like. List the asteroids that are moving towards the spaceship. So the spaceship is going to 600. Now, this one is going to look stationary with respect to the spaceship. This one is approaching the spaceship because it's going faster, so it's going to catch up to it. So it looks like B is 1. C for the same reason. D looks like it's going backwards. So spaceship is going forward. D is going slower, so it's going to look like the distance between them is going to keep increasing. It's going to spread apart. And spaceship is catching up to E, which also you can look at it this way. E is also catching up to the spaceship. So, and E. B, C, and E. Okay? List the asteroids that are moving away from the spaceship. Well, it cannot be B, C, and E, so let's see. A looks like it's stationary with respect to the spaceship. D looks like it's going backwards. In other words, the spaceship is running away from it. And I think I'm done. All right. See you later. Ciao.